Tonight on The Sleepy Scientist, we ray drifting gently toward our magnificent star to explore a profound cosmic awakening. NASA's discovery that the Sun's activity is ramping up after decades of decline. From the quiet solar minimum of 2008 to the growing activity that now stirs our star. We'll journey through the peaceful science of solar physics and discover what this awakening means for our technological world and cosmic neighborhood. In the eternal dance of our solar system, where planets glide through the darkness in their ancient orbits, there burns a luminous beacon that has sustained all life on Earth for over a billion years. Our sun, that magnificent golden orb that rises each morning to paint the sky with light, has been quietly stirring from what scientists believed might be a historic period of rest awakening, with renewed energy that ripples across the solar system. For centuries, astronomers have observed the mysterious rhythms of our star, noting how its surface activity waxes and wanes in cycles that seemed as regular as the turning of seasons. Yet recent discoveries have revealed that our sun follows patterns far more complex and unpredictable than the simple 11-year cycle that textbooks describe. In 2008, solar activity reached its lowest point in recorded history, leading scientists to wonder if our star was entering a prolonged period of quietude that might echo the great solar minimums of centuries past. But then something unexpected happened. Instead of continuing its descent into deeper slumber, the sun began to stir, slowly, gently, but with growing conviction. Our star started to show signs of renewed activity. Solar wind grew stronger, magnetic fields became more complex, and the subtle indicators of stellar awakening began to appear in the careful measurements made by spacecraft positioned throughout the solar system. Tonight, as we embark on this peaceful journey through the science of solar physics, we'll discover how NASA scientists detected this cosmic awakening and what it means for our planet and the entire solar system. We'll explore the gentle mechanisms that drive our star's behavior, from the deep nuclear furnace at its core to the magnificent coronal displays that crown its surface with ethereal beauty. The story we'll tell unfolds across multiple timescales, from the seconds-long explosions of solar flares to the centuries-long patterns of stellar activity that have shaped climate and civilization on Earth. We'll learn about the dedicated spacecraft that monitor our sun around the clock, the scientists who decode the subtle signals of solar behavior, and the technological systems on Earth that must adapt to our star's changing moods. As we begin this exploration, let us approach our sun with the reverence it deserves, not as a distant, impersonal ball of gas, but as the dynamic, living heart of our solar system, whose every pulse affects the space environment in which our planet travels. The sun's awakening represents more than a scientific curiosity. It reminds us of our intimate connection to the star that makes our existence possible. In the quiet darkness of space, where electromagnetic fields stretch across millions of miles and charged particles race at incredible speeds, our sun continues its ancient work of fusion and magnetism, creation and destruction. Tonight, we'll learn to hear the whispered songs of our star and understand the profound implications of its gentle awakening for our technological civilization and our place in the cosmic community. As we drift deeper into understanding our sun's awakening, let us first acquaint ourselves with the magnificent architecture of our star, the complex layered structure, stretching from the nuclear furnace at its core to the ethereal corona that extends millions of miles into space. Understanding the sun's anatomy provides the peaceful foundation for comprehending how activity patterns emerge and evolve within this cosmic powerhouse. At the very heart of our sun lies the core, a region of unimaginable density and temperature where hydrogen atoms fuse into helium in the process that has sustained our star for nearly 5 billion years. Here, in a space smaller than a quarter of the sun's radius, temperatures reach 15 million degrees Celsius, creating conditions so extreme that matter exists in a state unlike anything found on Earth. The pressure at the core is over 100 billion times that of our atmosphere, compressing matter to densities 13 times greater than lead. The nuclear fusion occurring in the core follows a delicate dance of quantum physics, where protons overcome their natural repulsion to combine and release tremendous amounts of energy. This energy begins a journey that will take thousands of years to reach the sun's surface. traveling through successive layers of stellar material, each with its own characteristics and behavior patterns that influence the solar activity we observe from Earth. Surrounding the core lies the radiative zone, a vast region where energy from fusion travels outward primarily through radiation. Photons created in the nuclear furnace begin their epic journey through this zone, but their path is far from straight. Each photon travels only a tiny distance before being absorbed and re-emitted by the dense plasma, creating a random walk that can take 100,000 years or more for energy to traverse this single layer. Of our star, the radiative zone extends from about 25% to 70% of the Sun's radius, creating a stable region where energy transport occurs slowly and smoothly. The temperature drops gradually from the core S extreme heat to about 2 million degrees. At the zone S outer boundary, this region remains relatively calm and unchanging, forming the stable foundation upon which the Sun's more dynamic outer layers operate. Above the radiative zone lies the convection zone, where the Sun's behavior becomes dramatically different and far more dynamic. Here, hot plasma rises toward the surface while cooler material sinks back toward the interior, creating vast convection cells that transport energy and drive many of the phenomena we associate with solar activity. These convection currents, some as large as Earth itself, constantly churn and mix the Sun's outer layers. The convection zone extends from about 70% of the Sun's radius to its visible surface, creating the turbulent, ever-changing environment where magnetic field lines become twisted and tangled. The interaction between convection and the Sun's rotation generates the complex magnetic fields that drive sunspots, solar flares, and other manifestations of solar activity. This zone represents the true powerhouse of solar variability. The photosphere, often called the Sun's surface, marks the boundary where the solar interior becomes transparent, and light can finally escape into space. This thin layer, only about 500 kilometers deep, glows with the familiar yellow-white light that illuminates our solar system. The temperature here drops to about 5,500 degrees Celsius, cool enough for some molecules to exist briefly before being torn apart by the intense radiation. Above the photosphere lies the chromosphere, a layer visible during solar eclipses as a reddish glow around the Sun's edge. This region shows increasing temperature with altitude, a phenomenon that initially puzzled solar physicists. The chromosphere reaches temperatures of about 20,000 degrees Celsius, heated by acoustic waves and magnetic phenomena generated in the layers below. Spicules, jet-like features of hot gas rise through the chromosphere like a forest of flame. The corona, the Sun's outer atmosphere, represents one of the most beautiful and mysterious regions of our star. Extending millions of kilometers into space, the corona glows with an ethereal light visible during total solar eclipses. Despite being farther from the nuclear furnace, the corona reaches temperatures exceeding 1 million degrees Celsius, heated by processes that scientists are still working to fully understand. The corona's structure changes dramatically with solar activity levels. During periods of low activity, it appears relatively smooth and symmetric, with long streamers extending into space. As activity increases, the corona becomes more complex and dynamic, filled with loops, prominences, and other structures that trace the Sun's magnetic field lines. These coronal features provide visible evidence of our star's magnetic complexity. The Sun's magnetic field permeates all these layers, generated by the complex interactions between rotation, convection, and electrical conductivity in the solar plasma. This magnetic field extends far beyond the visible Sun, creating the heliosphere, a vast magnetic bubble that encompasses the entire solar system and influences space weather throughout our cosmic neighborhood. The solar wind, a continuous stream of charged particles flowing from the corona, carries the Sun's magnetic field throughout the solar system at speeds of 300 to 800 kilometers per second. This wind interacts with planetary magnetic fields, creates the auroras we see on Earth and other planets, and determines the space environment that spacecraft must navigate. Understanding these layers and their interactions helps us comprehend how changes deep within the Sun eventually manifest as the surface activity and space weather that affect our planet. The awakening that NASA has detected involves subtle changes in magnetic field generation, convection patterns, and energy transport that influence every layer of our star's complex structure. As we continue our exploration of the Sun's awakening, we carry with us this image of our star as a layered, dynamic system where nuclear fire convection currents and magnetic fields interact to create the complex behavior patterns that have fascinated astronomers for centuries. Each layer contributes to the symphony of solar activity, from the steady nuclear rhythm of the core to the dramatic magnetic displays of the corona. Let's float gently toward one of the most enduring mysteries in astronomy, the solar cycle. That remarkably regular yet mysteriously complex rhythm by which our Sun's activity waxes and wanes over periods of approximately 11 years. This cosmic heartbeat has been recognized for centuries, yet it continues to surprise scientists with variations and complexities that challenge our understanding of stellar behavior and magnetic field generation. The discovery of the solar cycle began with observations of sunspots, those dark regions on the Sun's surface that have been visible to careful observers. Since ancient times, Chinese astronomers recorded sunspots over 2,000 years ago, noting their appearance and disappearance with the patient dedication that characterizes astronomical observation. However, it wasn't until the development of telescopes that systematic study of these solar features became possible. Galileo Galilei was among the first to study sunspots telescopically in the early 1600s, tracking their movement across the Sun's surface and noting their changing numbers and sizes. These early observations revealed that the Sun rotates and that its surface is not the perfect, unchanging sphere that ancient philosophy had imagined, but rather a dynamic star with features that appear and disappear in patterns that seemed almost organic in their complexity. The recognition of the solar cycle's periodicity came gradually, through the dedicated work of many astronomers over several centuries. Rudolf Wolf, a Swiss astronomer, developed the first systematic method for counting sunspots and tracking their numbers over time. His work in the mid-1800s revealed the approximately 11-year periodicity that characterizes the solar cycle, showing that periods of high sunspot activity alternate with periods of relative quiet in a pattern that seemed as regular as clockwork. The Wolf sunspot number, which counts both individual spots and groups of spots, became the standard measure of solar activity and remains one of the longest continuous scientific datasets in existence. This record reveals not only the basic 11-year cycle, but also longer-term variations that occur over periods of decades and centuries, suggesting that our Sun's behavior is governed by multiple overlapping cycles of different time scales. As our understanding of the Sun's structure developed, scientists realized that the solar cycle represents far more than simple changes in the number of dark spots on the solar surface. The cycle reflects fundamental changes in the Sun's magnetic field configuration, affecting everything from the corona's structure to the properties of the solar wind that flows throughout the solar system. During solar minimum, when sunspot numbers are lowest, the Sun's magnetic field takes on a relatively simple configuration, resembling a bar magnet with clear north and south poles. The corona appears smooth and symmetric, with long streamers extending into space mainly from the equatorial regions. Solar wind flows steadily but gently, and space weather events are relatively rare and mild. As the cycle progresses towards solar maximum, the Sun's magnetic field becomes increasingly complex and tangled. Sunspots appear in growing numbers, marking locations where strong magnetic fields emerge from the solar interior. Solar flares and coronal mass ejections become more frequent and powerful, sending bursts of energy and particles racing across the solar system toward Earth and other planets. The mechanism driving the solar cycle involves the complex interaction between the Sun's rotation and convection. Our star doesn't rotate as a solid body. Instead, its equatorial regions complete one rotation in about 25 days, while material near the poles takes about 35 days. This differential rotation continuously stretches and twists magnetic field lines, winding them up like rubber bands until they become unstable and break through the surface as sunspots. The solar dynamo theory explains how the Sun's rotation and convection work together to generate and regenerate the magnetic fields that drive solar activity. Deep within the convection zone, complex flows of conducting plasma act like a giant electrical generator, converting the energy of convection and rotation into magnetic energy that eventually emerges at the surface as the various phenomena of solar activity. However, the solar cycle is not perfectly regular, despite its apparent 11-year rhythm. Some cycles are stronger than others, producing more sunspots, more powerful flares, and more dramatic space weather. Some cycles last as short as 9 years or as long as 14 years. These variations suggest that the solar dynamo is influenced by factors that scientists are still working to understand fully. One of the most intriguing aspects of the solar cycle is the magnetic field reversal that occurs at each solar maximum. The Sun's north and south magnetic poles completely flip, with north becoming south and vice versa. This means that the complete magnetic cycle actually takes about 22 years, encompassing to 11-year sunspot cycles. This reversal process is gradual and complex, involving the reorganization of magnetic fields throughout the solar system. Long-term observations have revealed that the solar cycle itself undergoes longer-term variations. The amplitude and duration of individual cycles change over periods of decades and centuries, sometimes leading to extended periods of unusually high or low activity. These grand cycles suggest that multiple dynamo processes operate simultaneously within our Sun, creating complex interference patterns in solar activity. The Maunder minimum, a period from approximately 1645 to 1715, when sunspot activity was extremely low, represents one of the most dramatic examples of long-term solar variability. During this period, sunspots nearly disappeared entirely, and Earth experienced what is sometimes called the Little Ice Age. This connection between solar activity and terrestrial climate demonstrates the profound influence our star-S cycles can have on planetary environments. Modern space-based observations have revealed that the solar cycle affects far more than just sunspot numbers and magnetic field configurations. The total energy output of the Sun varies slightly but measurably over the cycle, with changes in both the total luminosity and the spectral distribution of solar radiation. These variations, while small in percentage terms, can have significant cumulative effects on planetary climates over long periods. The challenge of predicting solar cycle behavior remains one of the most important problems in solar physics. While the basic 11-year periodicity is well established, predicting the strength and timing of individual cycles has proven extremely difficult. Current predictions are based on complex computer models that attempt to simulate the solar dynamo process, but these models often disagree and frequently fail to match observed behavior. Recent cycles have shown particularly puzzling behavior that has challenged our understanding of solar physics. Cycle 23, which began in the late 1990s, was notably weak and long-lasting, leading to the profound solar minimum of 2008 that initially suggested our Sun might be entering a period of extended quiet. The subsequent awakening that NASA has detected represents a fascinating chapter in this ongoing story of solar cycle mysteries. As we continue our exploration of the Sun's recent awakening, we carry with us an appreciation for the remarkable complexity of our star-S magnetic cycles and the ongoing scientific quest to understand the mechanisms that drive solar activity. The solar cycle represents both the regularity and unpredictability that characterize our magnificent Sun, reminding us that even our closest star continues to hold mysteries waiting to be unraveled. Our peaceful journey now takes us to a pivotal moment in recent solar history, the remarkable solar minimum of 2008, when our Sun's activity dropped to the lowest levels ever recorded by modern instruments. This profound quietude in our star-S behavior created a cosmic silence so deep that scientists began to wonder if they were witnessing the beginning of an extended period of solar dormancy that might echo the great minimums of centuries past. The solar minimum of 2008 represented the culmination of a gradual decline in solar activity that had been developing for over 2 decades. Since the 1980s, careful measurements by spacecraft and ground-based instruments had shown a steady decrease In various indicators of solar activity, sunspot numbers declined, solar wind strength diminished, and the overall magnetic complexity of our star seemed to be winding down like a cosmic clockwork, running out of energy. By 2008, this decline had reached extraordinary levels. For 266 days that year, nearly 3/4 of the entire year, the sun showed no sunspots whatsoever. The visible face of our star appeared as a featureless golden disk, unmarked by the dark magnetic features that typically characterize periods of solar activity. This level of spotlessness had not been observed since reliable record-keeping began in the 18th century. The solar wind, that continuous stream of charged particles flowing from the sun throughout the solar system, reached its weakest levels ever measured. Spacecraft positioned at the L1 Lagrange point, where they maintain a constant view of the Sun-Earth system, detected solar wind speeds and densities that dropped to values scientists had never before observed with modern instruments. The usual pressure of this stellar breeze on planetary magnetic fields diminished to whispers. The magnetic field embedded in the solar wind also showed dramatic changes during this period. The strength of the interplanetary magnetic field, the extension of the Sun's magnetic field that pervades the solar system, dropped to levels that surprised researchers. This weakening had profound implications for the space environment throughout the solar system, affecting everything from cosmic ray penetration to the behavior of planetary magnetospheres. Perhaps most remarkably, the solar irradiance, the total amount of energy our sun radiates into space, reached its minimum values since satellite measurements began in the 1970s. While these changes amounted to only a fraction of a percent of the sun's total output, they represented measurable variations in the energy input to Earth's climate system and the other planets of our solar system. The extended nature of this solar minimum also broke records. Solar cycle 23, which reached its maximum around 1000, persisted far longer than the typical 11-year duration. The minimum conditions lasted from 2007 through 2009, creating an unusually prolonged period of solar quiet that delayed the onset of the next cycle by several years compared to historical averages. Space weather, the dynamic conditions in space influenced by solar activity, reached states of unprecedented calm during this period. The usual storms of charged particles, the spectacular auroral displays, and the electromagnetic disturbances that characterize active periods of the solar cycle diminished to gentle whispers. For spacecraft operators and satellite systems, this represented a period of unusual tranquility. In the normally turbulent space environment, the cosmic ray environment also changed dramatically. During the deep solar minimum, when solar activity is high, the enhanced magnetic fields and solar wind create a barrier that partially shields the solar system from high-energy cosmic rays originating from deep space. During the 2008 minimum, this shielding effect weakened significantly, allowing cosmic ray levels within the solar system to reach their highest values. In the modern space age, Earth's upper atmosphere responded to these changes in measurable ways. The thermosphere, the layer of atmosphere that extends from about 80 to 600 kilometers above Earth's surface, contracted significantly due to reduced heating from solar ultraviolet radiation. This contraction created less atmospheric drag on orbiting satellites, causing their orbits to decay more slowly than usual, a phenomenon carefully tracked by space agencies worldwide. Climate scientists watched the solar minimum with particular interest, studying its potential effects on Earth's weather patterns and long-term climate trends. While the direct radiative effects of solar variability are small compared to other climate factors, the extended minimum provided an opportunity to study how solar changes might influence terrestrial climate through complex atmospheric and oceanic interactions. The profound quiet of the 2008 solar minimum led some scientists to speculate that our sun might be entering a grand minimum similar to the Maunder minimum of the 17th century, when solar activity remained suppressed for several decades. Historical records suggest that such extended periods of solar quiet might be associated with significant climate changes on Earth, including cooler temperatures in certain regions. Solar physicists found themselves puzzled by the depth and duration of this minimum, computer. Models of the solar dynamo had not predicted such extreme conditions, suggesting that our understanding of the mechanisms driving solar activity might be incomplete. The minimum challenged existing theories about solar cycle prediction and highlighted the complexities of stellar magnetic field generation that scientists are still working to understand. International space agencies coordinated extensive observation campaigns during this period, recognizing the scientific opportunity presented by such unusual solar conditions. Multiple spacecraft, including the Solar and Heliospheric Observatory SOHO, the Advanced Composition Explorer ACE, and the Twin Solar Terrestrial Relations Observatory stereo probes, provided unprecedented detail about solar behavior during this quiet period. The heliosphere, the vast magnetic bubble created by the solar wind that encompasses the entire solar system, showed significant changes in size and structure during the minimum. Measurements from the Voyager spacecraft, traveling in the outer regions of the solar system, detected alterations in the heliosphere's boundaries that reflected the weakened solar wind conditions closer to the Sun. As 2008 progressed into 2009, scientists watched carefully for signs that the Sun might be stirring from its deep slumber. Small sunspots began to appear occasionally, and subtle changes in magnetic field measurements suggested that the next solar cycle might finally be beginning. However, the transition was slow and uncertain, with periods of renewed activity alternating with returns to minimum conditions. The deep solar minimum of 2008 ultimately became a watershed moment in solar physics, providing scientists with rare observational data about extreme solar quiet conditions and challenging theoretical understanding of solar cycle behavior. It set the stage for the subsequent discoveries about our Sun's awakening that would transform scientific understanding of stellar activity patterns and their implications for the space environment. As we prepare to explore NASA's groundbreaking discovery of the Sun's subsequent awakening, we carry with us the memory of this profound cosmic quiet, a reminder that our star, for all its apparent consistency, remains capable of surprising behavior that challenges our understanding and forces us to expand our knowledge of the magnificent, complex star that sustains all life in our solar system. As we drift deeper into the heart of our story, we encounter the moment of scientific revelation, NASA's groundbreaking discovery that our Sun, rather than continuing its descent into prolonged quietude, had begun a remarkable awakening that would challenge fundamental assumptions about stellar behavior and force scientists to reconsider their understanding of solar cycle dynamics and long-term stellar activity patterns. The discovery emerged from the careful analysis of data collected by a fleet of spacecraft that continuously monitor our Sun and the space environment throughout the solar system. Dr. Jamie Yasinski of NASA's Jet Propulsion Laboratory, leading a team of heliophysics researchers, noticed subtle but consistent patterns in the data that suggested something remarkable was happening to our star's behavior. The key insight came from examining long-term trends in solar wind measurements, collected by multiple spacecraft over more than 2 decades. While individual measurements showed the expected day-to-day and cycle-to-cycle variations typical of solar behavior, the long-term trend revealed a story that no one had anticipated. After declining steadily from the 1980s through 2008, solar activity parameters had begun to increase in ways that suggested a fundamental change in our star's behavior. The Advanced Composition Explorer ACE spacecraft, positioned at the L1 Lagrange point about 1.5 million kilometers from Earth toward the Sun, provided crucial data for this discovery. Since its launch in 1997, ACE has maintained a continuous vigil, measuring the properties of the solar wind, magnetic fields, and energetic particles flowing from our star. The spacecraft's long operational lifetime allowed researchers to detect trends that might have been missed by shorter missions. The WIND spacecraft, launched even earlier in 1994, provided additional confirmation of the trends that ACE was detecting. WIND's extended mission duration and stable orbit allowed it to serve as a crucial cross-reference for the patterns emerging in the data. Together, these spacecraft provided a consistent picture of solar wind evolution that spanned multiple solar cycles and captured the transition from declining to increasing activity. The analysis revealed that several key parameters of solar activity had reversed their long-term decline and begun increasing after 2008. Solar wind speed, which had been decreasing for decades, started to show a gradual but persistent upward trend. The magnetic field strength embedded in the solar wind similarly began to recover from its historic lows, suggesting that the sun's magnetic dynamo was strengthening after its period of unusual weakness. Plasma density measurements told a similar story. The number of charged particles per unit volume in the solar wind, which had dropped to unprecedented lows during the 2008 minimum, began showing signs of recovery and gradual increase. This parameter provides direct insight into the rate at which our sun is expelling material into space, reflecting the underlying magnetic and thermal processes occurring in the solar corona. Temperature measurements of the solar wind also contributed to the picture of solar awakening. The kinetic temperature of protons in the solar wind, which reflects the heating processes occurring in the solar corona, began showing increases that suggested more vigorous magnetic activity. In the sun's outer atmosphere, these temperature changes, while subtle, provided additional evidence that our star was stirring from its deep minimum. Perhaps most significantly, the research revealed that the solar magnetic field's complexity was increasing, rather than the simple, dipolar configuration characteristic of solar minimum conditions. Measurements showed growing evidence of the multipolar field structures associated with higher activity levels. This magnetic complexity provides the energy source for solar flares, coronal mass ejections, and other manifestations of solar activity. The timing of this reversal surprised the scientific community. Based on historical patterns and theoretical understanding of solar cycles, many researchers had expected the sun to continue its decline into what might have become a grand minimum lasting several decades. The fact that our star instead began showing renewed activity suggested that the mechanisms driving solar behavior might be more complex and less predictable than previously thought. Dr. Jasinski's team used sophisticated statistical analysis techniques to ensure that the trends they were observing represented genuine long-term changes rather than short-term fluctuations or instrumental effects. They applied multiple analytical methods to confirm that the reversal in solar activity was statistically significant and consistent across different measurement techniques and spacecraft. The discovery gained additional weight from observations made by other spacecraft and ground-based facilities. The Solar Dynamics Observatory (SDO), with its high-resolution imaging of the sun's surface and atmosphere, began detecting increased magnetic activity and more frequent emergence of magnetic flux from the solar interior. These observations provided visual confirmation of the statistical trends detected in solar wind measurements. International collaborations helped validate the findings. Data from European, Japanese, and other space agencies' missions showed consistent patterns that supported NASA's analysis. This global confirmation was crucial for establishing the credibility of such a significant claim about long-term solar behavior and ensuring that the discovery would withstand scientific scrutiny. The implications of this discovery extended far beyond academic interest in solar physics. The awakening sun suggested that space weather conditions would become increasingly active, with potential impacts on satellite operations, astronaut safety, radio communications, GPS systems, and power grids on Earth. Space weather prediction centers began incorporating these findings into their long-term forecasts and planning activities. The research also highlighted the importance of long-duration space missions for understanding stellar behavior. Without spacecraft like ACE and WIND that had operated for decades, detecting such long-term trends would have been impossible. The discovery demonstrated the value of maintaining continuous observations of our star and the space environment over multiple solar cycles. Publication of the findings in the Astrophysical Journal Letters marked a significant moment in solar physics, providing the first clear evidence that our sun had reversed its long-term decline and entered a new phase of increasing activity. The peer review process ensured that the methodology was sound and the conclusions were justified by the data, giving the scientific community confidence in these remarkable results. The discovery sparked renewed interest in solar cycle prediction and long-term stellar behavior. Researchers began developing new models that could account for the complex, non-linear behavior that the Sun was demonstrating. These efforts aimed to improve our ability to forecast solar activity and better understand the fundamental processes that drive stellar magnetic cycles. As news of the discovery spread through the scientific community and beyond, it captured public imagination and highlighted the dynamic nature of our nearest star. The Sun, often taken for granted as a stable source of light and heat, revealed itself once again as a complex, evolving system whose behavior continues to surprise and challenge our understanding of stellar physics and space weather dynamics. Let's float gently toward the most visible and historically significant indicators of our Sun's awakening sunspots, those mysterious dark regions on the solar surface that have served as humanity's window into stellar activity for centuries. These magnetic phenomena, appearing as dark blemishes against the Sun's brilliant photosphere, represent far more than simple surface features. They are direct manifestations of the powerful magnetic fields generated deep within our star's interior. Sunspots have fascinated human observers since ancient times, when Chinese astronomers first recorded their appearance as dark spots visible on the Sun during times of atmospheric haze or at sunrise and sunset. These early observers could not have imagined that they were witnessing one of the most fundamental processes in stellar physics, the emergence of magnetic flux tubes from the solar interior to create regions of intense magnetic field strength thousands of times greater than Earth's magnetic field. The systematic study of sunspots began with the telescope observations of Galileo Galilei in the early 1600s. Through careful tracking of these features across the solar disk, Galileo demonstrated that the Sun rotates and that its surface is not the perfect, unchanging sphere that Aristotelian philosophy had claimed. His observations revealed a dynamic star whose surface features appeared, evolved, and disappeared in patterns that suggested underlying physical processes of remarkable complexity. Modern understanding reveals sunspots as regions where strong magnetic fields suppress the normal convection processes that transport heat from the solar interior to the surface. The magnetic field lines emerging from the Sun's interior like invisible ropes create barriers that prevent hot plasma from rising efficiently. This magnetic suppression results in surface temperatures about 1,500 degrees Celsius cooler than the surrounding photosphere, causing these regions to appear dark by contrast. A typical sunspot consists of two distinct regions: the dark central umbra, where the magnetic field is strongest and most vertical, and the surrounding penumbra, characterized by a filamentary structure where magnetic field lines are inclined at various angles. The penumbra shows complex flows of material along magnetic field lines, creating the distinctive radial pattern visible in high-resolution solar images. Sunspots usually appear in pairs or groups connected by arching magnetic field lines that extend through the solar corona. These magnetic loops can be visualized as cosmic arcades, with one sunspot marking where field lines emerge from the solar interior, and another marking where they return. The magnetic connections between sunspot pairs create the energy storage systems that power solar flares and other manifestations of solar activity. The size of sunspots can vary dramatically, from tiny pores barely visible with the best telescopes to enormous groups larger than Jupiter. The largest sunspot groups can persist for weeks or even months as they rotate across the visible solar disk, providing extended opportunities for study and revealing the evolution of magnetic structures over time. Some groups become so large they can be seen with the naked eye when properly filtered solar viewing equipment is used. The number and distribution of sunspots follow the well-known 11-year solar cycle, but with fascinating variations that reflect the complex dynamics of the solar magnetic field. Early in the cycle, sunspots appear at relatively high latitudes in both hemispheres. As the cycle progresses, new spots emerge closer to the solar equator, following a pattern known as Spera's law that creates the distinctive butterfly diagram. When spot latitudes are plotted over time, the magnetic polarity of sunspot pairs follows Hale's polarity law, with leading and following spots having opposite magnetic polarities in each hemisphere. At the beginning of each new solar cycle, the magnetic polarities reverse compared to the previous cycle, creating a 22-year magnetic cycle that encompasses to 11-year sunspot cycles. This polarity pattern provides crucial clues about the solar dynamo processes operating within our star. During the profound solar minimum of 2008, sunspots nearly disappeared entirely from the solar surface. For 266 days that year, observers saw a blank solar disk unmarked by any visible magnetic activity. This extended absence of sunspots represented one of the most dramatic manifestations of the deep minimum conditions that had scientists wondering if our sun was entering a prolonged period of dormancy. As NASA's data began revealing the sun's awakening after 2008, sunspot observations provided visual confirmation of the statistical trends detected in solar wind measurements. New spots began appearing with gradually increasing frequency, marking the slow emergence of solar cycle 24. However, this cycle proved to be one of the weakest in over a century, with maximum sunspot numbers significantly lower than historical averages. The relationship between sunspot numbers and other indicators of solar activity provides insights into the complex processes driving our star's behavior. While sunspot counts serve as a convenient index of solar activity levels, they represent only one manifestation of the underlying magnetic processes. Other indicators, such as solar radio emissions, coronal brightness, and solar wind properties, sometimes show different patterns that reveal the multifaceted nature of solar variability. Modern space-based observations have revolutionized our understanding of sunspots by revealing their three-dimensional magnetic structure and temporal evolution with unprecedented detail. The Solar Dynamics Observatory provides continuous, high-resolution images that show sunspot development from emergence to decay, capturing the complex magnetic dynamics that occur within active regions over timescales from minutes to months. Helioseismology, the study of sound waves traveling through the sun, has revealed how sunspots are connected to magnetic structures extending deep into the solar interior. These acoustic investigations show that the magnetic fields associated with large sunspot groups can extend downward through the convection zone, possibly connecting to the magnetic dynamo processes operating at the interface between the convection and radiative zones. The prediction of sunspot cycles remains one of the most challenging problems in solar physics. While the basic 11-year periodicity is well established, forecasting the amplitude and timing of individual cycles has proven extremely difficult. The weak solar cycle 24 following the 2008 minimum defied many predictions, highlighting the limitations of current understanding and the need for improved theoretical models of solar magnetic field generation. Recent observations have revealed new types of magnetic activity on the sun that don't necessarily produce visible sunspots but still influence solar output and space weather. These spotless forms of activity include ephemeral active regions, coronal holes, and bright points that contribute to solar variability in ways that aren't captured by traditional sunspot counting methods. The ongoing solar cycle 25, which began around 2019, has shown interesting characteristics that may reflect the sun's awakening from its extended quiet period. While still relatively weak compared to the strong cycles of the late 20th century. So the cycle 25 has produced some notable sunspot groups and associated space weather events that suggest our star's magnetic dynamo is indeed strengthening after its period of unusual quietude. Understanding sunspots as manifestations of solar magnetic activity helps us appreciate their role as indicators of our star's overall health and behavior. These dark features serve as visible markers of invisible magnetic processes, providing a direct connection between observations available to amateur astronomers and the sophisticated theoretical understanding developed by professional solar physicists. As we continue our exploration of the sun's awakening, we carry with us an appreciation for sunspots as both beautiful phenomena in their own right and crucial indicators of the magnetic processes that drive solar activity. These dark windows into our star's magnetic soul continue to reveal new insights about stellar behavior and remind us that our Sun remains an active dynamic system whose mysteries are still being unraveled by patient observation and careful analysis. As we drift deeper into understanding our Sun's awakening, we encounter one of the most fundamental yet invisible phenomena of our solar system, the solar wind. That continuous stream of charged particles flowing from our star at incredible speeds, creating a dynamic space weather environment that pervades the entire heliosphere and influences every planet, moon, and spacecraft within our Sun's domain of influence. The solar wind represents the Sun's breath made manifest, carrying with it not just matter and energy, but also magnetic fields, electrical currents, and the very essence of our star's activity out into the cosmos. This stellar breeze flows continuously from the solar corona at speeds ranging from 300 to 800 kilometers per second, creating a supersonic stream that takes only a few days to travel from the Sun to Earth, carrying with it the information and influence of solar conditions. The discovery of the solar wind in the 1950s represented a revolutionary moment in our understanding of the solar system. Scientists had long known that comet tails always point away from the Sun, suggesting some form of solar influence, but the nature of this influence remained mysterious. Eugene Parker's theoretical work proposed that the solar corona must be continuously expanding into space, creating a permanent flow of material throughout the solar system. Early space missions confirmed Parker's predictions spectacularly. The Soviet Luna 2 and 3 missions in 1959, followed by NASA's Mariner to Venus flyby in 1962, provided the first direct measurements of solar wind particles and magnetic fields in interplanetary space. These measurements revealed a space environment far more dynamic and complex than anyone had imagined, filled with magnetic fields, electrical currents, and streams of charged particles flowing at tremendous velocities. The solar wind originates in the Sun's corona, where temperatures exceed 1 million degrees Celsius, so hot that not even the Sun's immense gravitational field can contain the expanding plasma. This superheated gas accelerates rapidly as it expands into space, reaching supersonic speeds within a few solar radii of the Sun's visible surface. The exact mechanisms driving this acceleration remain an active area of research, involving complex interactions between magnetic fields, thermal pressure, and wave heating processes to distinct types of solar wind flow from different regions of the solar corona. Fast solar wind, traveling at speeds of 600 to 800 kilometers per second, originates from coronal holes, regions where the Sun's magnetic field lines extend into space rather than looping back to the surface. Slow solar wind, moving at 300 to 400 kilometers per second, comes from the streamer belt regions where closed magnetic field lines create helmet-like structures in the corona. The composition of the solar wind provides a direct sample of solar material, allowing scientists to study the Sun's elemental and isotopic composition with remarkable precision. The wind consists primarily of protons and electrons, with small amounts of helium and trace quantities of heavier elements. Variations in composition reflect different source regions on the Sun and different acceleration processes, providing clues about coronal heating and solar magnetic field structure. Embedded within the solar wind flows the interplanetary magnetic field, the extension of the Sun's magnetic field throughout the solar system. This field follows a characteristic spiral pattern created by the combination of radial outflow and solar rotation, forming what scientists call the Parker spiral. The magnetic field carried by the solar wind creates the framework within which space weather phenomena develop and propagate throughout the heliosphere. The interaction between solar wind and planetary magnetospheres creates some of the most beautiful and dramatic phenomena in the solar system. When solar wind particles encounter Earth's magnetic field, they can be accelerated along field lines into the upper atmosphere, where they collide with atmospheric gases to create the spectacular auroral displays that illuminate polar skies with curtains of green, red, and blue light. During NASA's analysis that revealed the Sun's awakening, solar wind measurements played a crucial role in detecting the reversal from declining to increasing solar activity. The Advanced Composition Explorer and WIND spacecraft, positioned to continuously monitor solar wind conditions, detected subtle but persistent increases in wind speed, magnetic field strength, and particle density that indicated our star was stirring from its deep minimum state. The solar wind's magnetic field structure becomes more complex as solar activity increases. During quiet periods, the field maintains relatively simple patterns with clear sector boundaries where field polarity reverses. As activity rises, these patterns become more disturbed, with frequent rotations, enhanced field strengths, and irregular structures that reflect the increasing magnetic complexity of the solar corona. Space weather represents the collective term for the dynamic conditions in space created by solar wind variations and solar activity, just as Earth's weather results from atmospheric dynamics driven by solar heating. Space weather results from the solar wind's interaction with magnetic fields throughout the solar system. This space weather can range from gentle, steady conditions during solar quiet periods to violent storms during times of high solar activity. Geomagnetic storms represent one of the most significant forms of space weather affecting Earth. These disturbances occur when variations in the solar wind pressure or magnetic field orientation create enhanced coupling between the solar wind and Earth's magnetosphere. During severe storms, the resulting electromagnetic disturbances can affect satellite operations, radio communications, GPS accuracy, and even power grid stability. The radiation environment in space also varies dramatically with solar wind conditions and solar activity levels. During quiet periods, galactic cosmic rays high-energy particles from distant stellar explosions can penetrate relatively easily into the inner solar system. When solar activity increases, the enhanced magnetic fields and solar wind create better shielding, reducing cosmic ray levels, but increasing the flux of solar energetic particles from flares and other solar events. Modern society's dependence on space-based technology makes understanding and predicting space weather increasingly critical. Satellites providing GPS navigation, weather forecasting, telecommunications, and internet services all operate in the space environment shaped by solar wind conditions. Astronauts aboard the International Space Station face radiation exposure levels that vary significantly with space weather conditions, requiring careful monitoring and sometimes emergency procedures during severe storms. The heliosphere, the vast bubble created by the solar wind, extends far beyond the orbits of the planets, reaching distances of over 100 astronomical units from the Sun. The Voyager spacecraft, now traveling in interstellar space, have provided measurements of the heliosphere's boundary and the transition from solar wind-dominated space to the interstellar medium. These observations show how solar wind variations affect the entire structure of our local cosmic environment. Climate connections between solar wind variations and terrestrial weather patterns remain an area of active research, while the direct effects of solar wind on Earth's surface are minimal due to our protective magnetosphere and atmosphere. Indirect effects through atmospheric chemistry, cosmic ray variations, and electromagnetic coupling may influence climate systems in subtle but potentially significant ways over long time periods. The awakening solar activity detected by NASA suggests that space weather conditions will become increasingly dynamic in the coming years. Enhanced solar wind speeds, stronger magnetic fields, and more frequent disturbances will create a more turbulent space environment that space weather forecasters and satellite operators must prepare for. Understanding these changes is crucial for protecting technological systems and human activities in space. Future missions will continue expanding our understanding of solar wind physics and space weather dynamics. The Parker Solar Probe, humanity's first mission to touch the Sun, is providing unprecedented measurements of solar wind acceleration processes in the corona. The upcoming IMAP and SWFOL-1 missions will enhance our ability to monitor and predict space weather conditions, supporting both scientific understanding and practical space weather forecasting needs. As our exploration continues, we carry with us an appreciation for the solar wind as both a fundamental physical process and a practical influence on modern technological civilization. This invisible river of particles and magnetic fields connects us directly to our star, carrying the influence of solar conditions throughout the solar system and creating the dynamic space environment within which all space exploration and utilization must operate. Our peaceful journey now carries us to the most dramatic and powerful manifestations of our Sun's awakening coronal mass ejections and solar flares, those spectacular eruptions of energy and matter that represent the sudden release of magnetic energy stored in the solar corona. These phenomena showcase our star at its most dynamic, hurling billions of tons of plasma into space at speeds that can exceed 1,000 kilometers per second, creating space weather events that can be felt throughout the solar system. Solar flares represent the most energetic explosions in our solar system, releasing in minutes the equivalent of billions of hydrogen bombs. These sudden brightenings occur when magnetic field lines in the solar corona become twisted and tangled beyond their ability to maintain stable configurations. When these stressed magnetic structures suddenly reconnect and reorganize, they release enormous amounts of stored magnetic energy in processes that can heat plasma to temperatures of tens of millions of degrees. The energy released in major solar flares can equal the entire energy output of human civilization over several years, concentrated into a brief, brilliant flash that spans the electromagnetic spectrum from radio waves to gamma rays. The X-ray and extreme ultraviolet radiation from flares travels at the speed of light, reaching Earth in just over 8 minutes and immediately affecting our planet's upper atmosphere and ionosphere. Coronal mass ejections represent a different but related phenomenon, involving the actual expulsion of coronal material into interplanetary space. These eruptions can hurtle billions of tons of magnetized plasma across the solar system at speeds ranging from a few hundred to several thousand kilometers per second. When Earth lies in the path of a coronal mass ejection, the arrival of this solar material can trigger intense geomagnetic storms and spectacular auroral displays. The relationship between solar flares and coronal mass ejections is complex and not always predictable. While many large flares are accompanied by coronal mass ejections, some occur without associated mass ejections, and some coronal mass ejections occur without obvious flare signatures. This complexity reflects the intricate physics of magnetic energy storage and release in the solar corona, where multiple processes can lead to eruptive events. The classification of solar flares follows a logarithmic scale based on their peak X-ray intensity, as measured by Earth-orbiting satellites. C-class flares are minor events with little impact on Earth. M-class flares are moderate events that can cause brief radio blackouts and minor radiation storms, and X-class flares are major events capable of causing widespread radio blackouts, radiation storms, and power grid disruptions. The largest recorded flares have exceeded X20 in intensity, representing truly extraordinary releases of solar energy. During the deep solar minimum of 2008, both flares and coronal mass ejections became extremely rare, reflecting the overall quiet state of the solar magnetic field. The Sun's corona appeared relatively smooth and simple, with few of the complex magnetic structures needed to generate major eruptive events. This quiet period provided space weather forecasters with an unusual respite from the constant vigilance required during more active solar periods. As NASA's analysis revealed the Sun's awakening after 2008, the frequency and intensity of flares and coronal mass ejections began to increase gradually. So, the cycle 24, while overall weak compared to previous cycles, still produced notable eruptive events that demonstrated our star's return to more active behavior. These events provided valuable scientific data about the relationship between solar cycle progression and eruptive activity. The mechanisms driving solar eruptions involved the complex interplay between magnetic fields, plasma flows, and instabilities in the solar corona. Active regions, areas of enhanced magnetic field strength often associated with sunspot groups, serve as the primary sites for flare and coronal mass ejection production. The magnetic field lines in these regions can become highly twisted and sheared by solar surface motions, storing energy that can be explosively released when conditions become unstable. Magnetic reconnection represents the fundamental physical process underlying both flares and many coronal mass ejections. When oppositely directed magnetic field lines are brought together, they can suddenly reconnect, releasing the magnetic energy that was stored in the field configuration. This process can accelerate particles to high energies and heat plasma to extreme temperatures, creating the observed signatures of solar eruptive events. The propagation of coronal mass ejections through interplanetary space creates some of the most significant space weather phenomena affecting Earth and other planets. As these magnetized plasma clouds travel outward from the Sun, they can interact with the ambient solar wind, creating shock waves in compressed regions that enhance their geoeffectiveness. When they encounter planetary magnetospheres, the arrival of a coronal mass ejection at Earth typically occurs in stages, each with its own characteristic effects. The shock wave preceding the main plasma cloud can suddenly compress Earth's magnetosphere, triggering an initial response called a sudden impulse. The main body of the ejection, with its own magnetic field orientation, then interacts with Earth's field in ways that depend critically on the relative orientations of the two magnetic systems. When a coronal mass ejection carries a magnetic field oriented southward relative to Earth's field, the two field systems can couple efficiently, allowing solar wind energy to penetrate deeply into Earth's magnetosphere. This configuration can trigger intense geomagnetic storms characterized by dramatic auroral displays, satellite disruptions, radio blackouts, and, in extreme cases, power grid instabilities that can cause widespread electrical outages. The radiation environment created by solar flares poses particular challenges for space exploration and satellite operations. The high-energy protons accelerated by flare processes can penetrate spacecraft shielding and create hazardous radiation exposures for astronauts. During major solar particle events, astronauts aboard the International Space Station may need to shelter in the most protected areas of their spacecraft until radiation levels subside. Modern society's increasing dependence on space-based technology makes understanding and predicting solar eruptive events increasingly critical. GPS, satellites, communication systems, weather satellites, and internet infrastructure all depend on space-based assets that can be disrupted by intense solar activity. The economic impact of severe space weather events is estimated to reach billions of dollars. For extreme events affecting multiple technological systems simultaneously, forecasting solar flares and coronal mass ejections remains one of the most challenging problems in space weather prediction. While scientists can identify active regions with the potential for eruptive activity, predicting the exact timing, magnitude, and direction of specific events requires understanding magnetic field configurations and instabilities that are difficult to observe directly and model accurately. Recent advances in solar observations have improved our ability to study and potentially predict eruptive events. The Solar Dynamics Observatory provides continuous, high-resolution images of the solar corona and magnetic field evolution in active regions. The Solar Terrestrial Relations Observatory Stereo mission offers multiple viewpoints of coronal mass ejections, allowing scientists to track their three-dimensional structure and evolution as they propagate through interplanetary space. The Parker Solar Probe mission is providing unprecedented close-up observations of the solar corona and the early stages of flare and coronal mass ejection development. By flying closer to the Sun than any previous spacecraft, Parker is revealing the physical processes that accelerate and heat coronal plasma, potentially leading to better understanding and prediction of solar eruptive events. Ground-based solar observatories continue to play crucial roles in monitoring solar activity and providing early warning of potential space weather events. Networks of solar telescopes around the world maintain continuous surveillance of the Sun, tracking active region development and detecting the early signs of flare activity. These observations are crucial for space weather forecasting and protecting technological systems from solar disturbances. As the Sun continues its awakening from the deep minimum of 2008, space weather forecasters and satellite operators are preparing for increased activity levels and more frequent eruptive events. Understanding the characteristics and effects of solar flares and coronal mass ejections becomes increasingly important as our technological civilization becomes more dependent on space-based systems and more vulnerable to space weather disturbances. The study of solar eruptions also provides insights into fundamental plasma physics processes that occur throughout the universe. The conditions in the solar corona with its high temperatures, strong magnetic fields, and collisionless plasma are difficult or impossible to replicate in terrestrial laboratories. Solar observations thus serve as a natural laboratory for studying physics processes that occur in many other astrophysical environments. From stellar coronae to black hole accretion disks, let us drift gently back through the centuries to explore the profound historical periods when our Sun entered extended states of quietude, those remarkable epochs known as ground solar minimums that have shaped Earth's climate and human history in ways both subtle and dramatic. These extended periods of reduced solar activity provide crucial context for understanding the significance of our star's recent awakening and the complex patterns that characterize long-term stellar behavior. The most famous of these quiet periods is the Maunder minimum, which lasted from approximately 1645 to 1715, a 70-year stretch, during which sunspot observations showed that our Sun's visible activity nearly disappeared entirely. Named after the astronomer Edward Walter Maunder, who studied historical sunspot records in the late 19th century. This period coincided with some of the coldest decades of what historians call the Little Ice Age. During the Maunder minimum, careful observers recorded seeing sunspots on perhaps only 50 days throughout the entire 70-year period, a dramatic contrast to the thousands of sunspot observations typical of more active solar cycles. European astronomers, who had been systematically tracking solar activity since Galileo's telescopic observations began in the early 1600s, found themselves staring at a nearly featureless solar disk year after year, decade after decade. The climatic effects associated with the Maunder minimum were particularly severe in Europe and North America, where winters became notably harsher and growing seasons shorter. The River Thames in London froze regularly during winters, supporting elaborate frost fairs with merchants, entertainers, and even roasting oxen on the ice. Similar severe winters affected continental Europe, with reports of wine freezing in cellars and crops failing due to unseasonably cold temperatures. However, the relationship between solar activity and terrestrial climate during the Maunder minimum remains a subject of ongoing scientific investigation. While the timing correlation is compelling, the direct radiative effects of reduced solar activity are relatively small changes in total solar irradiance of perhaps 0.1 to 0.2%. Scientists continue studying how such small changes in solar output might be amplified through atmospheric and oceanic feedback mechanisms to produce the observed climatic effects. The Dalton minimum, spanning approximately from 1790 to 1830, represents another well-documented period of reduced solar activity. Named after the meteorologist John Dalton, this 40-year period showed sunspot numbers significantly below normal levels. Though not as dramatically suppressed as during the Maunder minimum, the Dalton minimum coincided with notable climate anomalies, including the famous year without a summer in 1816, when volcanic eruptions combined with low solar activity to create severe weather disruptions worldwide. Historical records from the Dalton minimum period include detailed observations by professional and amateur astronomers who documented the reduced sunspot activity and associated phenomena. These records showed that while solar activity was suppressed compared to normal levels, it didn't disappear entirely as it had during the more extreme Maunder minimum. This difference in severity provides insights into the range of possible solar minimum conditions and their associated effects. Earlier in history, the Spera minimum, occurring roughly from 1460 to 1550, represents another period of reduced solar activity inferred from proxy records, rather than direct observations. This period predates systematic telescopic sunspot observations, but evidence from radiocarbon isotope ratios in tree rings and cosmogenic isotopes in ice cores suggests significantly reduced solar activity levels. The Spera minimum also corresponded to particularly cold conditions in Europe and other regions. The Wolf minimum, spanning approximately from 1280 to 1350, provides evidence for even earlier periods of reduced solar activity. Again inferred primarily from cosmogenic isotope records, this minimum period coincided with the onset of the Little Ice Age and significant climatic disruptions throughout Europe and Asia. The correlation between multiple independent proxy records strengthens the case for genuine solar minimum conditions during this period. Medieval and ancient records provide additional evidence for variations in solar activity. Over longer timescales, Chinese astronomical records, which extend back over to millennia, include detailed accounts of sunspot observations and auroral sightings that can be used to infer historical solar activity levels. These records suggest that solar grand minimums occur irregularly, with typical intervals of several centuries between major minimum periods. The physical mechanisms responsible for grand solar minimums remain an active area of research. In solar physics, current theories suggest that these extended quiet periods may result from complex interactions between multiple dynamo processes operating within the Sun's interior. Computer models attempting to simulate solar dynamo behavior show that interactions between different magnetic field generation mechanisms can occasionally lead to destructive interference, suppressing overall solar activity for extended periods. Proxy records of solar activity, derived from cosmogenic isotopes produced by cosmic ray interactions in Earth's atmosphere, provide the longest-term perspective on solar variability. During periods of low solar activity, reduced magnetic shielding allows more cosmic rays to reach Earth's atmosphere, increasing the production of isotopes like carbon-14 and beryllium-10. These isotopes become incorporated into tree rings, ice layers, and sediments, creating permanent records of past solar activity levels. Analysis of cosmogenic isotope records spanning the past 10,000 years reveals that grand solar minimums occur roughly every few centuries, though with considerable irregularity in timing and duration. Some minimums last only a few decades, while others, like the Maunder minimum, persist for nearly a century. This variability suggests that the solar dynamo system can enter different types of suppressed states with varying degrees of stability. The deep solar minimum of 2008, while not reaching the extreme levels of historical grand minimums, shared some characteristics with these extended quiet periods. The nearly spotless solar disk, weakened magnetic fields, and reduced space weather activity echoed conditions described in historical accounts of the Maunder and Dalton minimums. This similarity led some scientists to speculate that our Sun might be entering a new grand minimum period. However, NASA's discovery of the Sun's awakening after 2008 suggests that our star avoided entering an extended grand minimum, at least for the present time. The reversal from declining to increasing activity indicates that whatever processes were driving the solar system toward minimum conditions were overcome by other factors that restored more typical solar behavior. This outcome highlights the unpredictable nature of long-term solar variability and the challenges involved in forecasting solar cycle evolution. The study of historical solar minimums has important implications for understanding potential future climate and space weather conditions. If our Sun were to enter another grand minimum similar to the Maunder minimum, the effects on Earth's climate and space environment could be significant. Reduced solar activity would likely lead to quieter space weather conditions, benefiting satellite operations but potentially allowing increased cosmic ray penetration to Earth's atmosphere and surface. Climate modeling studies attempt to quantify the potential effects of future solar grand minimums on Earth's temperature and weather patterns. While the direct radiative effects of reduced solar output are relatively small, studies suggest that indirect effects through atmospheric chemistry, ocean circulation, and cloud formation processes might amplify the climate response. However, these effects would likely be small compared to anthropogenic climate changes occurring simultaneously. The irregular occurrence of grand solar minimums makes them difficult to predict using current understanding of solar dynamo physics. While scientists can identify conditions that might favor the onset of minimum periods, the complex Non-linear nature of the solar magnetic field generation process makes long-term forecasting extremely challenging. Continued observations and improved theoretical understanding will be necessary to develop reliable prediction capabilities. For these extended solar quiet periods, understanding historical solar minimums also provides perspective on the normal range of solar variability and the resilience of Earth's climate and biological systems to changes in solar output. Life on Earth has persisted through multiple grand minimums, demonstrating the buffering capacity of atmospheric and oceanic systems. However, human technological civilization, with its dependence on satellite systems and electrical grids, may be more vulnerable to extreme space weather variations than natural systems. As we continue our exploration of the Sun's recent awakening, we carry with us the knowledge that our star is capable of extended periods of unusual behavior that can persist for decades or centuries. The historical record of grand solar minimums reminds us that solar variability encompasses much more than the familiar 11-year cycle, and that our Sun remains capable of surprising behavior that challenges our understanding and affects conditions throughout the solar system. We're drifting gently toward our magnificent star, our Sun, as it slowly stirs from what scientists thought might be a deep, prolonged slumber. Imagine, if you will, floating peacefully through the cosmos, approaching our solar system's heart with the same gentle patience that astronomers have shown. While watching our Sun for centuries, there's something profoundly soothing about contemplating stellar rhythms. These vast cosmic clockworks that tick away on scales so much grander than our earthly concerns. Recent research from NASA has revealed something quite unexpected about our Sun's behavior, something that changes our understanding of the next several decades of solar activity. It's a story that unfolds like a slow, cosmic awakening, not dramatic or alarming, but rather like watching a sleeping giant gradually open its eyes after what appeared to be the beginning of a very long nap. For the past 2.5 decades leading up to 2008, our Sun had been steadily quieting down. Scientists observed a gentle decline in sunspot activity, a softening of the solar wind, and an overall dimming of our star's more energetic outbursts. This wasn't unusual in itself. The Sun follows an 11-year cycle of activity rising and falling in a rhythm that astronomers have tracked since Galileo first pointed his telescope skyward and noticed those dark spots moving across our star's face. But what made this period special was its duration and depth. The decline wasn't just part of the normal cycle. It seemed to suggest something much more significant. The solar minimum of 2008 was profound, what scientists called a deep solar minimum. For 266 of 2008's 366 days, our Sun showed no sunspots at all. It was as if our star had decided to take a particularly restful pause. This deep quiet reminded astronomers of other historic periods when the Sun seemed to withdraw its energy for extended periods. There was the Maunder minimum from 1645 to 1715, 70 years when sunspots virtually disappeared, coinciding with what became known as the Little Ice Age. There was also the Dalton minimum from 1790 to 1830, another 4-decade stretch of reduced solar activity. Given this historical context and the steady decline leading up to 2008, many scientists began to wonder if we were witnessing the beginning of another grand solar minimum. The evidence seemed to point that way. All the indicators suggested our Sun might be settling in for a prolonged period of reduced activity that could last decades or even centuries. Jamie Jasinski from NASA's Jet Propulsion Laboratory described it perfectly. All signs were pointing to the Sun going into a prolonged phase of low activity. The scientific community was preparing for what might have been a historic lull in solar activity, perhaps comparable to those earlier minimum periods that had such profound effects on Earth's climate and space environment. But then, something unexpected happened. In 2008, just when the Sun reached its deepest quiet in recorded history, something shifted. Like a sleeper who stirs just when you think they've settled in for the night. Our star began to show signs of increased activity. It wasn't dramatic at first, just subtle changes in the solar wind, gentle increases in magnetic field strength, and a gradual uptick in the energetic particles streaming from our star. This reversal was so unexpected that it took years of data analysis to confirm what was happening. Scientists had to carefully examine multiple sources of information. Data from the Advanced Composition Explorer ACE mission launched in the 1990s. Observations from the WIND spacecraft that has been monitoring solar activity for decades, and measurements from a whole fleet of heliophysics missions designed to study our Sun's influence throughout the solar system. What they found was remarkable. Since 2008, every major indicator of solar activity has been steadily increasing. The solar wind, the constant stream of charged particles flowing from our Sun, has been growing stronger. The magnetic field embedded in this wind has been intensifying. The number and intensity of sunspots have been climbing beyond what scientists expected based on previous cycles. This isn't just about the normal 11-year sunspot cycle, which we call solar cycle 25. That cycle has its own rhythm, its own predictable rise and fall. What NASA discovered goes deeper. It's a longer-term trend that spans multiple cycles, a gradual awakening that seems to be building momentum year by year. The current solar cycle 25, which officially began in December 2019, has surprised forecasters at every turn. Initially predicted to be relatively weak, similar to the previous cycle, it has instead been more active than expected. We've reached solar maximum, the peak of activity, earlier than predicted, and with more intensity than models suggested. But again, this isn't cause for alarm. Think of it like watching someone gradually wake up from a deep sleep. There might be some stretching, some movement under the blankets, a gradual increase in breathing rate. Our Sun is doing something similar on a cosmic scale. The increased activity manifests as more frequent solar flares, those bright eruptions of energy from the Sun's surface, and more coronal mass ejections, where our star occasionally throws vast bubbles of plasma out into space. These events, while more frequent now than during the deep minimum of 2008, are still part of the Sun's natural behavior. Our star has been producing flares and ejections for billions of years. What's changed is the trend. Instead of declining into another grand minimum as many expected, our Sun appears to be entering a phase of sustained higher activity. This awakening creates what we might call space weather. Just as Earth has weather systems driven by our planet's rotation and atmospheric dynamics, the space around Earth experiences weather driven by our Sun's magnetic field and particle emissions during periods of increased solar activity. This space weather becomes more dynamic, more energetic. The Advanced Composition Explorer has been particularly valuable in tracking this awakening. Positioned at a gravitationally stable point between Earth and the Sun, about 1.5 million kilometers away, ACE acts like a sentinel, continuously monitoring the solar wind and providing advance warning of space weather events. The data it has collected over more than 2 decades tells the story of our Sun's slow awakening with remarkable clarity. The WIND mission, launched even earlier, has provided an even longer baseline of observations. Together, these spacecraft and others in NASA's heliophysics fleet have created a comprehensive picture of how our Sun's activity has been changing. The data shows not just the 11-year cycles, but these longer-term variations that can span decades or even centuries. What makes this awakening particularly interesting from a scientific perspective is that we don't fully understand why it is happening. Solar physics, despite decades of study, still holds many mysteries. We understand the basic mechanisms. The Sun's magnetic field, generated by the complex motions of plasma in its interior, drives all of this activity. But the longer-term variations, the reasons why our star sometimes becomes more or less active over periods of decades, remain partly mysterious. This uncertainty isn't troubling, it's actually one of the most fascinating aspects of solar science. Our Sun, despite being the closest star and the most studied object in our solar system after Earth itself, continues to surprise us. It reminds us that we're still learning, still discovering, still being amazed by the complexity and beauty of cosmic processes. The gradual nature of this awakening is actually quite soothing when you think about it. This isn't a sudden, dramatic change, but rather a slow, steady process unfolding over years and decades. It's like watching the seasons change, but on a much grander time scale. The increases in solar activity are measured and gradual, giving us plenty of time to observe, understand, and adapt. From our perspective here on Earth, this awakening means we're entering an era where space weather will likely be more active than it has been in recent decades. We can expect more frequent auroras, those beautiful displays of light that occur when charged particles from the Sun interact with Earth's magnetic field and atmosphere. We can expect more dynamic conditions in the space around our planet, which affects satellites and space missions. But this increased activity also means more opportunities for scientific discovery. Every solar flare, every coronal mass ejection, every fluctuation in the solar wind provides new data, new insights into how our star works. The upcoming missions, IMOP, Carruthers Geocorona Observatory, and SWFOL-1, will provide unprecedented opportunities to study this awakening sun in detail. As we drift through these contemplations of our slowly waking star, there's something profoundly peaceful about recognizing our place in these cosmic rhythms. We're witnessing something that unfolds on timescales far beyond human lives, yet affects our daily existence in subtle ways. Our sun's gentle awakening is a reminder that we're part of something much larger than ourselves, connected to stellar processes that have been unfolding for billions of years. The story of our sun's awakening is still being written. Each day brings new observations, new data, new insights into how our star is changing. Scientists around the world continue to monitor and analyze these changes, building our understanding piece by piece, like assembling a vast cosmic puzzle. In the quiet moments of contemplating this stellar awakening, we can find a deep sense of connection to the cosmos. Our sun, which provides the energy for all life on Earth, is slowly stirring from what appeared to be the beginning of a long slumber. Instead, it seems to be gathering energy for a more active phase that may last for decades to come. This awakening touches every aspect of our solar system. The solar wind, growing stronger year by year since 2008, shapes the boundaries of our heliosphere, that vast bubble of solar influence that surrounds our entire solar system. As our sun becomes more active, this boundary shifts and changes, affecting how cosmic rays from interstellar space enter our solar neighborhood. The beauty of studying these slow, cosmic processes is that they put our daily concerns into perspective. While we worry about tomorrow's weather or next week's plans, our sun operates on timescales that stretch across decades and centuries. There's something deeply calming about contemplating these vast rhythms, these stellar processes that unfold with such patience and persistence. As we continue our gentle journey through the science of our awakening sun, we'll explore how this increased activity affects our technological civilization, how it influences the space environment around Earth, and what it means for future human exploration of the solar system. But for now, we can simply rest in the knowledge that our star is slowly, gently waking up, bringing with it new possibilities for discovery and wonder. The data continues to flow in from our fleet of solar-watching spacecraft, each measurement adding to our understanding of this slow awakening. Scientists analyze these observations with the same patience that the sun shows in its gradual changes, carefully, thoughtfully, building understanding step by step across years and decades. As we continue our gentle exploration of our slowly waking sun, let us turn our attention to how this stellar awakening touches our daily lives here on Earth. In ways both subtle and profound, the increased solar activity we've been observing since 2008 doesn't remain confined to the depths of space. Like ripples spreading across a cosmic pond, the effects of our sun's awakening travel the 150 million kilometers to Earth, carrying with them changes that influence our technological civilization in fascinating and sometimes challenging ways. Consider, if you will, the vast network of satellites that now orbit our planet like a constellation of artificial stars. At this very moment, as you rest and listen to these words, thousands of spacecraft are circling Earth, their solar panels drinking in sunlight, their electronic systems processing signals, their orbits maintained by careful calculations that account for the subtle influences of our planet's atmosphere and magnetic field. These satellites have become integral to our modern way of life in ways we rarely stop to consider. They carry our phone calls across oceans, guide our navigation systems, monitor our weather, and beam entertainment and information to billions of people. Yet these technological marvels exist in an environment that is far from the vacuum we might imagine space to be. They swim, in a sense, through the constantly flowing stream of particles we call the solar wind. As our sun awakens and this solar wind grows stronger, satellites face increasing challenges. The charged particles streaming from our star can interfere with their electronic systems, creating what engineers call single-event upsets, moments, when a high-energy particle strikes a computer chip and flips a bit of data, potentially causing a satellite to reset or malfunction temporarily. These interactions happen with a gentle randomness that mirrors the stochastic nature of the solar wind itself. Most of the time, satellite systems are robust enough to recover from these minor disruptions automatically. But as solar activity increases, these events become more frequent, requiring more careful monitoring and more sophisticated protective systems. The effects become more pronounced during periods of heightened space weather, when our sun releases particularly energetic bursts of particles and magnetic fields. During these times, satellite operators must sometimes make difficult decisions, whether to temporarily shut down sensitive systems, adjust orbits to minimize exposure, or accept increased risk in order to maintain critical services. One of the most subtle but pervasive effects of increased solar activity is atmospheric heating. When the sun becomes more active, it emits more high-energy radiation, particularly in the extreme ultraviolet spectrum. This radiation is absorbed by Earth's upper atmosphere, causing it to heat up and expand like a vast, invisible balloon. This expansion creates increased atmospheric drag on satellites in low Earth orbit. Those spacecraft flying between about 160 and 2,000 kilometers above our planet's surface. The effect is gentle but persistent. Satellites gradually lose altitude as they encounter more atmospheric resistance, requiring occasional boosts to maintain their proper orbits. During periods of high solar activity, this atmospheric drag can become so significant that it affects the operational lifetimes of satellites. Some spacecraft designed to operate for 5 or 10 years might find their missions shortened if they cannot compensate for the increased drag. In extreme cases, satellites have been lost entirely when atmospheric heating exceeded their ability to maintain orbit. The February 2022 loss of 40 Starlink satellites serves as a poignant example of how space weather can affect our technological infrastructure. These satellites were deployed during a period of increased solar activity that caused significant atmospheric heating. The expanded atmosphere created more drag than the newly deployed satellites could overcome, causing them to re-enter Earth's atmosphere and burn up, a $50 million lesson in the power of space weather. But satellites are not the only technological systems affected by our sun's awakening. Here on Earth's surface, beneath the protective blanket of our atmosphere and magnetic field, we might think ourselves immune to solar influences. Yet the effects reach us here as well, through subtle but important pathways. Our planet's electrical power grids represent one of the most critical and vulnerable systems during periods of enhanced space weather. The process by which solar activity affects power grids is both elegant and complex, involving the intricate dance between solar magnetic fields and Earth's own magnetic environment. When the sun releases a coronal mass ejection, one of those vast bubbles of plasma and magnetic field that occasionally burst from our star's surface, it travels through space carrying its own magnetic field. If this field happens to be oriented opposite to Earth's magnetic field when it arrives, something remarkable happens. The two fields can connect and merge in a process called magnetic reconnection. This reconnection allows solar energy to flow into Earth's magnetosphere, the magnetic bubble that surrounds our planet. The energy creates electric currents that flow through the upper atmosphere and, through electromagnetic induction, can create currents in conductors on Earth's surface, including the long-distance transmission lines that carry electricity across continents. These geomagnetically induced currents are typically small, measured in amperes per kilometer of transmission line, But power grids are vast networks stretching across thousands of kilometers. So, even small currents per unit length can add up to significant effects. The currents can cause transformers to overheat, protective systems to malfunction, and in extreme cases, widespread power outages. The most famous example of this phenomenon occurred on March 13, 1989, when a severe geomagnetic storm caused the collapse of Hydro-Quebec's power grid, leaving 6 million people without electricity for 9 hours. The storm induced currents that saturated transformers and triggered protective systems throughout the network, creating a cascade failure that propagated across the entire grid in less than 90 seconds. But such dramatic events are rare. Most of the time, the effects of space weather on power grids are much more subtle. Small fluctuations in voltage, minor increases in transformer heating, OCCASIONAL false alarms in protective systems. Utility companies have learned to monitor space weather forecasts and take preventive measures during periods of increased solar activity, such as reducing power loads or temporarily taking sensitive equipment offline. The vulnerability of power grids to space weather has actually decreased in some ways. As technology has advanced, modern protective systems are faster and more sophisticated than those of previous decades. However, our dependence on electrical power has also grown dramatically, making any disruption potentially more consequential for society. GPS and other satellite navigation systems face their own unique challenges from space weather. These systems work by precisely timing radio signals as they travel from satellites to receivers on Earth. The signals must pass through the ionosphere, that layer of charged particles in Earth's upper atmosphere. And space weather can cause fluctuations in the ionosphere that affect signal propagation. During periods of enhanced solar activity, the ionosphere becomes more turbulent and variable. Radio signals can be delayed, refracted, or even temporarily blocked entirely. This can cause GPS receivers to lose lock on satellites, produce inaccurate position readings, or fail to function altogether. For applications that require high precision, such as aircraft landing systems, surveying equipment, or autonomous vehicles, these disruptions can be critical. The effects on GPS illustrate one of the most interesting aspects of space weather, its ability to link solar processes with terrestrial technology. Through the medium of Earth's atmospheric layers, the sun's increased activity heats and ionizes the upper atmosphere, changing its radio propagation characteristics, which in turn affects the precision of navigation systems that millions of people rely on every day. Radio communications face similar challenges during periods of enhanced space weather. High-frequency radio waves, used for long-distance communication, reflect off the ionosphere to reach receivers beyond the horizon. When space weather disturbs the ionosphere, these reflections can become unpredictable, causing radio blackouts that can last from minutes to hours. These blackouts particularly affect aviation, where pilots rely on high-frequency radio for communication during transoceanic flights. During severe space weather events, aircraft may need to alter their routes to maintain communication with air traffic control, sometimes adding significant time and fuel costs to flights over polar regions where the effects are most pronounced. The International Space Station and other crewed spacecraft require special consideration. During periods of enhanced space weather, astronauts are exposed to higher levels of radiation during these events, sometimes requiring them to shelter in the most protected parts of their spacecraft. Mission controllers must carefully monitor space weather forecasts and may delay spacewalks or other activities if conditions become too hazardous. For the astronauts aboard the ISS, space weather creates both challenges and opportunities. The increased radiation poses health risks that must be managed through careful monitoring and protective procedures. But the enhanced auroral activity also provides spectacular viewing opportunities. Astronauts often photograph the dancing curtains of light that appear when charged particles from the sun interact with Earth's magnetic field and atmosphere. The economic implications of space weather on our technological systems are substantial, though they're often hidden. The insurance industry estimates that severe space weather events could cause billions of dollars in damage to satellites, power grids, and other infrastructure. More commonly, the gradual effects, shortened satellite lifetimes, increased maintenance costs, occasional service disruptions, create ongoing expenses that are built into the operating costs of modern technological systems. Airlines routinely adjust flight paths during space weather events, sometimes flying at lower altitudes or taking more southerly routes, to avoid the worst effects of radiation and communication disruptions. These adjustments cost fuel and time, but are necessary to maintain safety margins. During periods of enhanced solar activity, the financial markets, increasingly dependent on satellite communications and precise timing systems, must also account for space weather risks. High-frequency trading systems that rely on GPS for precise time synchronization can be affected by ionospheric disturbances, potentially leading to trading errors or system malfunctions. As our Sun continues its slow awakening, these technological interactions will likely become more frequent and more significant. The trend toward increased solar activity that began in 2008 suggests we may be entering a period where space weather effects on technology become more routine rather than exceptional events. This doesn't mean we should be concerned about our technological civilization collapsing under solar assault. Rather, it means we need to develop more sophisticated ways of living with space weather. Much as we have learned to live with terrestrial weather, weather forecasting allows us to prepare for storms, adjust our activities, and protect vulnerable systems. Similarly, space weather forecasting is becoming increasingly sophisticated, allowing operators of critical systems to take preventive measures when solar storms are predicted. The development of space weather forecasting represents one of the most fascinating intersections of solar science and practical technology. Scientists now monitor the Sun continuously using a fleet of spacecraft, watching for the early signs of solar flares and coronal mass ejections. When potentially significant events are detected, warnings are issued to satellite operators, power grid controllers, airlines, and other affected industries. The Advanced Composition Explorer ACE spacecraft, positioned between Earth and the Sun, serves as our primary early warning system for space weather. When a coronal mass ejection passes ACE, scientists can predict when it will reach Earth, typically 15 to 60 minutes later, and estimate its potential effects on our technological systems. This advance warning, though brief, is often enough to take protective measures. The upcoming space weather follow-on Lagrange 1 SWFOL-1 mission will continue and enhance this early warning capability, providing more sophisticated measurements of the solar wind and magnetic field. Combined with ground-based observations and computer models, these spacecraft observations allow scientists to provide increasingly accurate space weather forecasts. As we contemplate the effects of our slowly waking Sun on our technological civilization, there's something both humbling and inspiring about recognizing our vulnerability to stellar processes. Our most sophisticated technologies, our global communications networks, our power grids and navigation systems, all can be influenced by events happening 150 million kilometers away on the surface of our star. Yet this vulnerability also represents opportunity. Each space weather event provides new data, new insights into how solar processes affect technological systems. Engineers develop more robust designs, operators create better protective procedures, and scientists improve their forecasting capabilities. In this way, our technological civilization is gradually adapting to live in harmony with the natural rhythms of space weather. The story of space weather effects on technology is still being written. As our Sun continues its awakening, new challenges will undoubtedly emerge as we deploy new technologies, from megaconstellations of small satellites to increasingly autonomous systems that rely on precise navigation. But human ingenuity has consistently found ways to work with natural phenomena rather than against them. In the gentle contemplation of these technological challenges and adaptations, we can find a deeper appreciation for the intricate connections that bind our modern world to cosmic processes. Every time we use GPS navigation, make a satellite phone call, or simply turn on an electric light, we participate in a vast technological system that must account for the influence of our slowly waking Sun. As we continue our peaceful journey through the cosmos of solar science, Let us now turn our gentle attention to those brave souls who venture beyond Earth's protective embrace, and how we safeguard them from the growing influence of our slowly awakening star. There is something profoundly moving about human beings choosing to leave the safety of our planet's magnetic cocoon and venture into the vast ocean of space. These modern explorers, astronauts aboard the International Space Station, crews of future lunar missions, and the pioneering souls who will one day journey to Mars, face challenges that would have been unimaginable to earlier generations of explorers. Unlike terrestrial explorers who must contend with weather, terrain, and the availability of food and water, space travelers must also protect themselves from an invisible but ever-present danger: radiation. This radiation comes from multiple sources: cosmic rays from deep space energetic particles trapped in Earth's radiation belts, and increasingly as our sun awakens, solar particle events that can flood the space environment with dangerous levels of high-energy particles. The challenge of protecting astronauts from radiation is both a deeply technical problem and a profoundly human one. It requires understanding the complex physics of how energetic particles interact with matter, the biological effects of radiation exposure, and the engineering challenges of creating lightweight, effective shielding for spacecraft. But at its heart, it's about ensuring that human beings can safely explore the cosmos and return home healthy. To understand radiation protection in space, we must first contemplate the nature of the radiation environment beyond Earth's atmosphere. Our planet's magnetic field and atmosphere create a remarkably effective shield against most space radiation. The magnetic field deflects charged particles, sending them harmlessly around our planet, while the atmosphere absorbs and scatters radiation that might otherwise reach the surface. But this protection has limits. The magnetic field is strongest near the equator and weakest near the poles, creating regions where radiation can penetrate more easily. There are also gaps and disturbances in the field, particularly during periods of enhanced space weather when our awakening sun sends strong gusts of particles and magnetic field toward Earth. Astronauts aboard the International Space Station orbit at an altitude of about 400 kilometers, still within the outer fringes of Earth's protective magnetosphere. Yet even at this relatively protected location, they experience radiation levels hundreds of times higher than people on Earth's surface. During their 6-month missions, ISS crew members typically receive radiation doses equivalent to several years of natural background radiation on Earth. The sources of this radiation are varied and fascinating in their cosmic origins. Galactic cosmic rays are high-energy particles, primarily protons and heavier atomic nuclei that originate from exploding stars and other violent events throughout our galaxy. These particles travel at nearly the speed of light and carry enormous amounts of energy. When they strike spacecraft or human tissue, they can cause significant damage at the cellular level. So the cosmic rays represent another radiation source, and one that becomes increasingly important as our sun awakens. During solar particle events, sudden releases of high-energy particles from our star, the radiation environment in space can become dramatically more hazardous. These events can occur with little warning and can persist for hours or days, creating dangerous conditions for astronauts. The biological effects of radiation exposure in space are complex and not fully understood. Unlike the brief, high-dose exposure that might occur during a medical X-ray, space radiation represents chronic exposure to relatively low doses over extended periods. The particles are also much more energetic than typical medical radiation, capable of penetrating deep into tissue and causing more severe cellular damage. Radiation can damage DNA directly, breaking chemical bonds and disrupting the genetic code that controls cellular function. It can also create free radicals, highly reactive molecules that can cause additional damage throughout the cell. Over time, this damage accumulates and can lead to cancer, cataracts, cardiovascular disease, and other health problems. The most immediate concern during solar particle events is acute radiation syndrome, the collection of symptoms that can occur when someone receives a high dose of radiation in a short period. Symptoms can include nausea, fatigue, and more severe effects that could incapacitate an astronaut when they most need to be alert and capable. But space agencies have developed sophisticated strategies for protecting astronauts from these radiation hazards, strategies that must balance effectiveness with the practical constraints of spaceflight. Every gram of shielding material that goes into space costs thousands of dollars to launch, so protection systems must be as lightweight and efficient as possible. The International Space Station incorporates multiple layers of radiation protection, starting with its basic structure. The station's aluminum hull provides some shielding against lower-energy particles, while specialized areas offer enhanced protection during radiation events. The Unity module, for example, has areas surrounded by additional shielding materials including water containers and equipment that can help block radiation. During severe space weather events, its crew members can take shelter in the most protected areas of the station. These refuges are typically located in the center of the station's modules, surrounded by as much mass as possible. Water is particularly effective as a shielding material because hydrogen nuclei are very efficient at stopping energetic particles through elastic collisions. The station's water supply, stored in flexible containers, can be arranged around sleeping quarters or work areas to create temporary radiation shelters. Food supplies, spare equipment, and even waste materials can contribute to radiation shielding when positioned strategically. This approach, sometimes called storm sheltering, allows crews to significantly reduce their radiation exposure during the most dangerous periods. Mission controllers on Earth continuously monitor space weather conditions and can alert crews to take shelter when dangerous radiation events are predicted or detected. The Advanced Composition Explorer and other spacecraft provide early warning of solar particle events, giving crews precious minutes to hours to prepare for increased radiation levels. Personal radiation monitoring is another critical component of astronaut protection. Each crew member wears multiple dosimeters, small devices that measure accumulated radiation dose over time. These provide real-time information about radiation exposure and help mission controllers make decisions about crew activities and protective measures. The dosimeters also contribute to our long-term understanding of radiation exposure in space. Data from hundreds of astronaut missions over decades has helped scientists develop better models of space radiation and its biological effects, informing the design of future protection systems and mission planning. Looking beyond the ISS to future deep space missions, radiation protection becomes even more challenging. Lunar missions will take astronauts beyond Earth's magnetic field entirely, exposing them to the full intensity of galactic cosmic rays and solar radiation. The Moon itself offers no magnetic protection, though lunar soil can provide effective shielding for surface habitats. NASA's Artemis program, which aims to return humans to the Moon, incorporates advanced radiation protection strategies from the earliest design phases. The Orion spacecraft that will carry crews to lunar orbit includes a radiation storm shelter, a specially shielded area where crew members can take refuge during solar particle events. The shelter uses a combination of materials to stop different types of radiation. Polyethylene, a hydrogen-rich plastic, is particularly effective against energetic protons, while metals like aluminum provide protection against lower-energy particles. The design must balance weight constraints with protection effectiveness, requiring careful optimization of materials and configuration. For surface operations on the Moon, astronauts will rely on spacesuits with enhanced radiation protection and habitat designs that incorporate lunar resources for shielding. Underground habitats or structures covered with lunar regolith soil can provide excellent protection against radiation while using materials available on the Moon itself. Mars missions represent the ultimate challenge in radiation protection. The journey to Mars takes 6 to 9 months each way, during which astronauts would be exposed to the full intensity of space radiation. With no possibility of emergency return to Earth's protection, Mars itself has no significant magnetic field and only a thin atmosphere, providing minimal natural radiation protection. Mission planners are developing strategies that include both passive shielding, physical materials that absorb radiation, and active protection systems that might use magnetic fields to deflect charged particles away from spacecraft. Some designs incorporate storm shelters similar to those planned for lunar missions, while others propose using consumables like water and food as disposable shielding materials. The psychological aspects of radiation protection are as important as the technical ones. Astronauts must live and work while constantly aware of invisible radiation that could affect their health both immediately and in the long term. Training programs help crews understand radiation risks and protective procedures, while maintaining the confidence and focus needed for complex missions. Research continues on both Earth and in space to improve radiation protection systems. Scientists study how different materials interact with space radiation, develop new lightweight shielding concepts, and investigate biological countermeasures that might help the human body better cope with radiation exposure. Some of the most promising research involves understanding how radiation affects different individuals. Genetic factors appear to influence radiation sensitivity, and future missions might include personalized radiation protection based on individual crew members' genetic profiles and medical histories. Pharmaceutical countermeasures represent another area of active research. Drugs that could protect against radiation damage or help repair cellular damage after exposure are being developed and tested. These could provide additional protection beyond physical shielding, particularly for long-duration missions where weight and space constraints limit shielding options. The development of advanced materials offers hope for more effective and lighter radiation shielding. Carbon nanotube composites, advanced ceramics, and smart materials that could adapt their protective properties based on radiation conditions are all being investigated. Some concepts even propose using waste products from the spacecraft's life support systems as shielding materials. Electromagnetic shielding represents a futuristic but potentially revolutionary approach to radiation protection. By creating artificial magnetic fields around spacecraft, it might be possible to deflect charged particles, much as Earth's magnetic field protects our planet. While current technology makes such systems heavy and power-intensive, ongoing research might eventually make them practical for space missions. As our Sun continues its slow awakening, the importance of radiation protection for space travelers will only increase. The enhanced solar activity we've observed since 2008 means more frequent and potentially more intense solar particle events, creating additional challenges for mission planners and protection system designers. But these challenges also drive innovation and discovery. Each advance in radiation protection technology, each new understanding of how radiation affects human biology, each improved forecasting capability for space weather events, brings us closer to making long-duration human space exploration safer and more sustainable. The story of radiation protection in space is ultimately a story of human determination to explore beyond our planetary boundaries while maintaining the safety and health of the explorers. It represents one of the most sophisticated examples of how we adapt technology to work within natural cosmic processes, rather than trying to overcome them entirely. The astronauts and cosmonauts who currently orbit Earth aboard the International Space Station serve as pioneers in learning to live and work in the radiation environment of space. Their experiences, carefully monitored and documented, provide the knowledge foundation for protecting future explorers who will venture to the Moon, Mars, and eventually to destinations throughout our solar system. In contemplating these brave explorers and the systems designed to protect them, we can find both inspiration and humility. Inspiration in the human drive to explore and discover, and humility in recognizing our dependence on technological systems to survive in the cosmic radiation environment that pervades space beyond Earth's protective embrace. The gentle rhythm of research and development in radiation protection continues day by day, year by year, building the knowledge and technology foundation that will enable humanity to become a true spacefaring species. Each experiment, each mission, each advance in our understanding brings us closer to that goal while ensuring that those who venture into space can do so safely and return home healthy. As we drift peacefully through our exploration of our Sun's awakening, let us now turn our contemplative gaze toward the future, toward the remarkable fleet of spacecraft that will soon join the cosmic dance of solar observation, each designed to help us understand our star's slowly changing behavior. There is something deeply satisfying about the way scientific exploration builds upon itself, generation by generation, mission by mission. Each spacecraft that has studied our sun, from the pioneering missions of decades past to the sophisticated observatories currently watching our star, has added layers to our understanding, like sedimentary rock formation but in the realm of knowledge rather than geology. Now, as our sun continues its unexpected awakening from what many thought might be a prolonged quiet period, humanity is preparing to launch a new generation of solar observatories. These missions, the Interstellar Mapping and Acceleration Probe IMAP, the Carruthers Geocorona Observatory, and the Space Weather Follow-on Lagrange 1 SWFOL1, represent the next chapter. In our ongoing dialogue with our home star, each of these missions was conceived and designed during the period when scientists expected our sun might be entering a deep, prolonged minimum. Now, as they prepare for launch into an era of increasing solar activity, they will provide unprecedented opportunities to study our sun during its slow awakening, offering insights that were impossible when these missions were first envisioned. Let us begin our gentle exploration with IMAP, the Interstellar Mapping and Acceleration Probe, a mission that embodies the beautiful interconnectedness of cosmic processes. Scheduled to launch no earlier than September 23rd, 2025, IMAP will venture to one of the most fascinating locations in our solar system, the first Lagrange point, where the gravitational forces of Earth and the Sun balance in perfect equilibrium. From this vantage point, approximately 1.5 million kilometers sunward of Earth, IMAP will study the boundary between our solar system and interstellar space. This boundary, called the heliosphere, is shaped by the solar wind, the constant stream of particles flowing from our sun. As our star awakens and the solar wind strengthens, this boundary shifts and changes, affecting how cosmic radiation from other stars enters our solar neighborhood. IMAP carries 10 sophisticated instruments, each designed to study different aspects of how particles and magnetic fields behave at the edge of our solar system. The mission will map the three-dimensional structure of the heliosphere, track how energetic particles are accelerated to nearly the speed of light, and monitor how our sun's changing activity affects the space environment throughout the solar system. The beauty of IMAP's mission lies in its ability to connect processes happening on our sun's surface with effects that extend far beyond the planets. When our sun releases a coronal mass ejection or experiences a period of enhanced activity, the effects propagate outward at the speed of the solar wind, eventually reaching and reshaping the boundary with interstellar space. IMAP will observe these connections in real time, providing a comprehensive view of how solar activity influences our entire cosmic neighborhood. One of IMAP's most intriguing capabilities is its ability to study energetic neutral atoms, hydrogen atoms that carry information about the structure and dynamics of the heliosphere. These atoms form when charged particles from the solar wind interact with neutral hydrogen atoms from interstellar space, creating a faint but measurable signature that IMAP's instruments can detect and analyze. By mapping these energetic neutral atoms, IMAP will create the first comprehensive three-dimensional map of our heliosphere. This map will show how the bubble of solar influence changes shape and size as our sun's activity varies, providing crucial insights into how stellar activity affects the space environment around OT, her stars throughout the galaxy. The mission will also study cosmic rays, those high-energy particles from deep space that can affect everything, from climate patterns on Earth to the health of astronauts. As our sun awakens and the solar wind strengthens, it becomes more effective at deflecting cosmic rays away from the inner solar system. IMAP will observe this process directly, measuring how solar activity modulates the cosmic ray environment throughout our solar neighborhood. Accompanying IMAP on its journey will be to smaller but equally important missions, the Carruthers Geocorona Observatory and SWFOL1. These spacecraft will ride as secondary payloads on the same launch, demonstrating the efficiency and elegance of modern mission planning. The Carruthers Geocorona Observatory, named after the pioneering ultraviolet astronomer George Carruthers, will study Earth's geocorona, the faint glow of hydrogen atoms that extends far beyond our planet's atmosphere. This might seem like a purely Earth-focused study, but the geocorona actually serves as a sensitive indicator of space weather conditions. When solar activity increases, it affects how Earth's upper atmosphere interacts with space, changing the distribution and behavior of hydrogen atoms in the geocorona. By monitoring these changes, Carruthers will provide new insights into how space weather affects our planet's atmospheric system, complementing ground-based and low-orbit observations with a unique perspective from the L1 point. The observatory will use ultraviolet imaging to map the geocorona S structure and monitor how it changes during different space weather conditions. These observations will help scientists understand how Earth's atmosphere responds to variations in solar activity, providing crucial information for predicting space weather effects on satellite operations and atmospheric chemistry. Carruthers represents a beautiful example of how space science often reveals unexpected connections between seemingly different phenomena. What begins as a study of Earth's atmospheric glow becomes a tool for understanding space weather, which in turn helps us comprehend our Sun's influence on planetary environments throughout the solar system. The third member of this cosmic trio is SWFOL-1, the Space Weather Follow-on Lagrange 1 mission, developed by NOAA to provide operational space weather monitoring and forecasting. While IMAP and Carruthers focus primarily on scientific discovery, SWFOL-1 has the practical mission of protecting our technological civilization from the effects of space weather. SWFOL-1 will serve as our primary early warning system for dangerous space weather events. Positioned at the L1 point alongside IMAP and Carruthers, it will monitor the solar wind continuously, providing 15 to 60 minutes of advance warning when potentially hazardous conditions are heading toward Earth. The spacecraft carries instruments designed to measure the speed, density, and magnetic field orientation of the solar wind, as well as the flux of energetic particles that can damage satellites and endanger astronauts. When SWFOL-1 detects the signature of an incoming coronal mass ejection or solar particle event, it will immediately transmit warnings to Earth, allowing satellite operators, power grid controllers, and other affected parties to take protective measures. The importance of SWFOL-1 becomes even greater as our Sun continues its awakening. The increased frequency and intensity of space weather events expected in the coming decades will make reliable forecasting crucial for protecting our increasingly space-dependent civilization. SWFOL-1 represents the operational face of solar science, the practical application of decades of research to real-world challenges. The mission will also contribute to scientific understanding by providing high-quality, continuous measurements of space weather conditions. These data will help scientists improve their models of how solar disturbances propagate through space and affect different technological systems, leading to better forecasting capabilities and protection strategies. What makes this trio of missions particularly exciting is how they will work together to provide complementary perspectives on our Sun's awakening. IMAP will study the large-scale effects of solar activity on the heliosphere. Carruthers will monitor how space weather affects Earth's atmospheric system, and SWFOL-1 will provide real-time warnings of dangerous conditions. The timing of these launches, during our Sun's slow awakening from the 2008 minimum, could not be more fortuitous. These missions will observe solar activity as it continues to increase, providing unprecedented data about how our star's behavior affects everything, from the edge of the solar system to Earth's upper atmosphere. The L1 point where these missions will operate represents one of the most strategically important locations in space science, discovered by the 18th century mathematician Joseph Louis Lagrange. These points of gravitational equilibrium allow spacecraft to maintain stable positions relative to Earth and the Sun with minimal fuel expenditure. L1 is particularly valuable for solar observation because spacecraft there can maintain continuous view of the Sun without Earth ever blocking their line of sight. They also sample the solar wind before it reaches Earth, providing crucial advance warning of space weather events. The L1 point has hosted a continuous presence of space weather monitoring spacecraft for decades, making it one of humanity's most important outposts for understanding solar-terrestrial interactions. The advanced instruments aboard these new missions represent significant improvements over previous generations of space weather monitors. SWFO-L1's particle detectors can measure a wider range of energies with greater precision, while its magnetometer can detect more subtle variations in the solar wind's magnetic field. These improvements will enable more accurate forecasting of space weather effects and better understanding of the physical processes involved. IMAP's instrument suite is particularly sophisticated, designed to study phenomena that range from individual atomic interactions to large-scale magnetic field structures spanning billions of kilometers. The mission's energetic neutral atom imagers can create movies showing how the heliosphere changes over time, while its particle analyzers can determine the composition and energy distribution of cosmic rays with unprecedented precision. The data from these missions will flow to scientists around the world, contributing to a global effort to understand our sun's behavior and its effects throughout the solar system. International collaboration has become increasingly important in space science, with researchers from multiple countries working together to analyze observations and develop theoretical models. Future solar missions beyond this initial trio are already being planned and proposed. Concepts under consideration include closer approaches to the Sun than ever before achieved, multi-spacecraft formations that could provide three-dimensional views of solar phenomena, and specialized missions to study specific aspects of solar physics in greater detail. The European Space Agency's Solar Orbiter mission, launched in 2020, is already providing complementary observations from a unique perspective that includes views of the Sun's polar regions, combined with data from the Parker Solar Probe, which is making progressively closer approaches to our star, and observations from Earth-based solar telescopes. We are entering an era of unprecedented comprehensive solar observation. The beauty of this expanding fleet of solar observatories lies in how each mission contributes unique pieces to our understanding of our star's complex behavior. No single spacecraft can observe all aspects of solar activity, but together they create a comprehensive picture that no individual mission could achieve alone. As these missions begin their operations during our Sun's continuing awakening, they will undoubtedly make discoveries that we cannot currently anticipate. The history of solar physics is filled with unexpected findings that have revolutionized our understanding, from the discovery of the solar wind itself to the recognition of solar cycles and the complex magnetic processes that drive solar activity. The instruments and techniques being deployed on IMAP, Carruthers, and SWFO-L1 are sensitive enough to detect phenomena that may not have been observable with previous generations of spacecraft. As our Sun becomes more active, these missions may reveal new aspects of solar behavior that were invisible during the quieter periods when earlier missions operated. The data these missions collect will also contribute to our understanding of other stars throughout the galaxy. Our Sun is the only star we can study in detail, so understanding how it works provides crucial insights into stellar physics in general. As we discover more about how our own star's activity affects its surroundings, we develop better models for understanding how other stars influence their planetary systems. In contemplating these future missions and the discoveries they may make, there is something deeply satisfying about humanity's patient, persistent effort to understand our cosmic environment. Generation after generation of scientists and engineers have built upon previous knowledge, each adding their own contributions to our collective understanding. The gentle persistence of scientific exploration mirrors in some ways the slow, patient processes we observe on our Sun itself. Just as our star's awakening unfolds over years and decades, our understanding of solar physics develops through the accumulated observations and insights of many missions spanning many years. As we prepare for the launch of these new solar observers, we can rest in the knowledge that human curiosity and ingenuity continue to expand our ability to comprehend the cosmos around us. These missions represent not just technological achievements, but expressions of our deep desire to understand our place in the universe and our relationship with the star that makes all life on Earth possible. As we continue our gentle journey through the cosmos of solar science, Let us now expand our contemplation to encompass the vast sweep of stellar time, considering not just our sun's current awakening, but its entire life story, past, present, and the distant future that stretches across billions of years. There is something profoundly peaceful about contemplating processes that unfold on stellar time scales, where changes that seem momentous to us represent mere moments in the life of a star. Our sun's current awakening, significant as it is for our technological civilization and space weather, is but a tiny fluctuation in a stellar lifetime that spans 10 billion years or more. To understand our sun's place in the grand scheme of stellar evolution, we must first appreciate the remarkable journey it has already taken. Our star formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust in what was then a much younger galaxy. This stellar nursery, enriched with heavy elements forged in the hearts of previous generations of stars, provided the raw materials for our sun and the planetary system that would eventually evolve around it. The process of stellar birth is both violent and beautiful, as gravity gradually overcomes the random motions of gas particles in an interstellar cloud, pulling them together into an increasingly dense and hot core. When the temperature and pressure at the center reach critical thresholds, nuclear fusion ignites. Hydrogen nuclei overcome their natural repulsion and fuse together to form helium, releasing enormous amounts of energy in the process. This moment of first fusion marked our sun's arrival on what astronomers call the main sequence, the long, stable phase of a star's life when it burns hydrogen in its core. Our sun has been in this phase for its entire 4.6 billion year existence, and it will remain there for approximately 5 billion more years, slowly consuming the hydrogen fuel that powers its nuclear furnace. During this main sequence phase, our sun has been remarkably stable by stellar standards. Its energy output has increased gradually over time by about 30% since it first began burning hydrogen, but this increase has been so slow as to be nearly imperceptible on human timescales. The 11-year solar cycles we observe, and the longer-term variations like our sun's current awakening, are tiny oscillations superimposed on this vast underlying stability. This stability has been crucial for the development of life on Earth. Had our sun been more variable, with dramatic changes in energy output over geological time, Earth's climate would have fluctuated too wildly for complex life to evolve. Instead, our star has provided a steady energy source that has allowed oceans to remain liquid and atmospheres to develop and persist across billions of years. The current variations in solar activity that we observe, the sunspot cycles, the longer-term trends like the awakening since 2008, even the grand minima like the Maunder minimum, all occur within this envelope of basic stellar stability. They represent changes in the sun's magnetic field and outer layers rather than fundamental alterations to the nuclear fusion processes in its core. Understanding these magnetic variations requires contemplating the complex dynamics of plasma, matter so hot that electrons are stripped from atomic nuclei, creating a fluid of charged particles that responds to magnetic forces. The sun's interior is entirely plasma, and the movements of this electrically conducting fluid generate magnetic fields through a process called the dynamo effect. The sun's dynamo operates on multiple time scales simultaneously. The 11-year sunspot cycle reflects one mode of this magnetic dynamo, while longer variations, including the current awakening phase, may involve different aspects of the same fundamental process. Scientists are still working to understand how these different magnetic cycles interact and influence each other. The solar dynamo is driven by the sun's rotation and the complex convective motions in its outer layers. Hot plasma rises from the interior, cools as it approaches the surface, then sinks back down to be reheated, creating vast circulation patterns that stretch the sun's magnetic field lines and amplify magnetic fields through electromagnetic induction. These dynamo processes may operate on timescales much longer than the 11-year cycle we're familiar with. Some theories suggest cycles lasting centuries or even millennia, which could explain phenomena like the grand solar minima observed in historical records. Our sun's current awakening may represent part of such a longer-term cycle, though the evidence remains incomplete. As we contemplate these vast magnetic cycles, it's humbling to realize how much remains mysterious about our own star. Despite being the most studied object in astronomy after Earth itself, our Sun continues to surprise scientists with unexpected behavior. The recent awakening that began in 2008 is just the latest example of our star's capacity to confound predictions and reveal new aspects of stellar behavior. But even these magnetic mysteries pale in comparison to the dramatic changes that await our Sun in the distant future. In approximately 5 billion years, our star will exhaust the hydrogen fuel in its core, marking the end of its main sequence lifetime and the beginning of a transformation that will fundamentally alter the solar system. When the hydrogen fuel runs out, nuclear fusion will continue in a shell surrounding the now helium core. But this shell burning is less stable than core fusion. The energy output will fluctuate, and the Sun's outer layers will begin to expand as they reheated by the increasingly energetic shell burning beneath. Over the course of about 1 billion years, our Sun will evolve into a red giant star, expanding to perhaps 100 times its current diameter. The surface will cool as it expands, giving the star a reddish color. But the total energy output will actually increase dramatically. The solar system will be transformed beyond recognition during this phase. Mercury will almost certainly be engulfed and vaporized as the Sun's outer layers expand. Venus may suffer the same fate, depending on exactly how large the Sun becomes and how much mass it loses through stellar winds. During the expansion, Earth's fate is less certain. It may survive as a scorched, lifeless world orbiting within the Sun's extended atmosphere, or it may spiral inward and be destroyed. But these dramatic events lie so far in the future that they become almost abstract when viewed from our current perspective. 5 billion years is longer than Earth has existed, longer than complex life has inhabited our planet, longer than the age of most of the familiar constellations we see in our night sky. It is a span of time that dwarfs all of human history, and makes even geological time seem brief by comparison. During this red giant phase, our Sun will lose a significant fraction of its mass through powerful stellar winds. These winds will carry away the outer layers of the star, enriching interstellar space with the heavy elements that formed in the Sun's interior. Through nuclear fusion, carbon, nitrogen, oxygen, and other elements essential for life will be returned to the galaxy, eventually becoming part of new generations of stars and planets. After spending roughly 1 billion years as a red giant, our Sun will undergo a series of thermal pulses as different fusion processes ignite and die out in its interior. Helium fusion will begin when the core becomes hot and dense enough, creating carbon and oxygen. These processes will be highly unstable, leading to dramatic variations in the Sun's energy output and further mass loss. Through stellar winds, eventually, our Sun will shed its outer layers entirely in a series of explosive events, creating what astronomers call a planetary nebula, a beautiful, glowing shell of gas illuminated by the hot core that remains behind. These nebulae, despite their name, have nothing to do with planets. They're called planetary nebulae because they appeared round and planet-like in early telescopes. The core left behind after this mass ejection will be a white dwarf star, an incredibly dense object about the size of Earth but containing roughly 60% of our current Sun's mass. A teaspoon of white dwarf matter would weigh as much as a car on Earth's surface. This white dwarf will be initially very hot, glowing white hot from the residual heat of its formation, but it will have no internal energy source. Over billions upon billions of years, this white dwarf remnant of our Sun will slowly cool, fading from white to yellow to red and eventually to a cold, dark object called a black dwarf. This cooling process takes so long that no black dwarfs are thought to exist yet in the universe. The cosmos isn't old enough for any white dwarf to have cooled completely. This stellar life cycle, main sequence star to red giant, to planetary nebula to white dwarf to black dwarf, represents the fate of stars like our Sun. More massive stars follow different evolutionary paths, sometimes ending their lives in spectacular supernova explosions that can outshine entire galaxies. For weeks or months, less massive stars burn their fuel more slowly and may remain on the main sequence for tens or even hundreds of billions of years. Our Sun occupies a middle ground in stellar evolution, neither the most dramatic nor the most long-lived of stars. This moderate nature has been crucial for the development of life on Earth. Very massive stars burn too quickly and end too violently to provide stable environments for billions of years. Very low-mass stars might provide longer-lived energy sources, but they also present challenges for planetary habitability. The elements that make up our bodies and our world were forged in the nuclear furnaces of stars like our Sun, and in the more violent hearts of massive stars that ended their lives in supernovae. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were created through stellar nuclear synthesis and returned to space. When earlier generations of stars completed their evolutionary journeys, this cosmic recycling process has been operating throughout the galaxy's 13.8 billion year history, gradually enriching interstellar space with the heavy elements needed for rocky planets and complex chemistry. Our Sun is what astronomers call a population-ized star, relatively rich in heavy elements because it formed from material that had already been processed through previous generations of stellar evolution. When our Sun eventually completes its own evolutionary journey and returns much of its mass to interstellar space, it will contribute to this ongoing process of cosmic chemical evolution. The elements created in our Sun's core during its 10 billion year lifetime will become part of future stars, planets, and perhaps even future forms of life that we cannot currently imagine. The timescales involved in stellar evolution provide a unique perspective on our current observations of solar variability. The awakening we've observed since 2008, significant as it may be for space weather and technological systems, represents an infinitesimally small fluctuation in our Sun's overall evolutionary timeline. Yet understanding these short-term variations is crucial for comprehending the complex physical processes that govern stellar behavior. Solar physics research contributes not only to our understanding of our own star, but to stellar astrophysics in general. Our Sun is the only star we can study in detail. We can observe its surface features, measure its magnetic fields, and monitor its activity patterns with a precision impossible for more distant stars. These detailed observations of our Sun provide the foundation for understanding how stars in general behave and evolve. The magnetic dynamo processes we observe on our Sun likely operate in similar ways in other solar-type stars throughout the galaxy. The activity cycles, the magnetic field reversals, the stellar winds and particle emissions, all of these phenomena probably occur around countless other stars, affecting their surrounding planets and space environments in ways we're only beginning to understand. Studying our Sun's long-term evolution also helps us understand the habitability of exoplanets around other stars. As we discover thousands of planets orbiting distant suns, we need to understand how stellar evolution affects planetary environments over geological time. How do stellar activity cycles influence planetary atmospheres? How do changes in stellar energy output affect the potential for liquid water and stable climates? Our Sun's future evolution will eventually make Earth uninhabitable, but this process will unfold so slowly that it provides no immediate concern for human civilization. More pressing are the shorter-term variations in solar activity, like the current awakening, that can affect our technological systems and space exploration efforts over time scales of decades to centuries. The study of solar evolution also connects us to the broader story of cosmic evolution. Our Sun, formed from material enriched by previous generations of stars, lived a stable main sequence lifetime that enabled the development of complex life and will eventually return processed material to the galaxy for future star formation. This cosmic recycling represents one of the most profound and beautiful aspects of astrophysics. As we contemplate our Sun's place in this vast evolutionary story, we can find both humility and wonder. Humility in recognizing that our star, remarkable as it is to us, represents just one of hundreds of billions of stars in our galaxy alone. Wonder in appreciating the precise conditions and stable behavior that have made our Sun's warmth and energy available for the 4.6 billion years it took for life to evolve and flourish on Earth. The current awakening of our Sun, viewed against this backdrop of stellar evolution, becomes part of a much larger story of cosmic change and continuity. Our star continues its patient burning of hydrogen fuel, maintaining the nuclear fires that have warmed Earth for billions of years, while also displaying the complex magnetic behavior that creates the space weather phenomena we observe and study. In the gentle contemplation of these vast time scales and cosmic processes, we can find a deep peace that comes from understanding our place in the universe's grand story. We are made of stellar material, warmed by stellar energy, and connected through physical processes to the vast community of stars that fills our galaxy, and the observable universe beyond. As we approach the gentle conclusion of our cosmic journey, let us now weave together all the threads of solar science we've explored, creating a tapestry that reveals the profound interconnectedness of our slowly awakening star with every aspect of our existence. There is something deeply satisfying about reaching this point in our exploration, where all the individual elements we've contemplated, our sun's unexpected awakening, its effects on technology and human space exploration, the protective missions we're launching, and the vast sweep of stellar evolution begin to form a coherent, beautiful whole that speaks to the fundamental unity of cosmic processes. Our journey began with the surprising discovery that our sun, rather than entering the prolonged quiet period many scientists expected, has instead been slowly awakening since 2008. This awakening manifests in strengthening solar winds, increasing magnetic field activity, and more frequent space weather events. What seemed like the beginning of a deep stellar slumber has transformed into a gradual stirring that continues to surprise researchers with its persistence and implications. This solar awakening connects directly to every technological system we depend upon in our modern world. The satellites that carry our communications, guide our navigation, and monitor our weather all exist within the stream of particles and magnetic fields flowing from our star. As this stream intensifies with our sun's awakening, these spacecraft face increasing challenges that require ever more sophisticated protection and operational strategies. The power grids that distribute electricity across continents, the GPS systems that guide everything from smartphones to autonomous vehicles, the radio communications that connect aircraft with ground control, all of these terrestrial technologies must account for the invisible influence of our sun's changing magnetic field. Space weather, once an obscure scientific specialty, has become an essential consideration for maintaining our technological civilization. The brave astronauts who venture beyond Earth's protective magnetosphere face the most direct effects of our sun's awakening. The increased radiation environment requires carefully designed shielding systems, sophisticated monitoring equipment, and operational procedures that balance scientific and exploration goals with crew safety. As humanity prepares for longer missions to the Moon and eventually to Mars, understanding and protecting against space radiation becomes increasingly critical. The future missions we've explored, IMAP, Carruthers Geocorona Observatory, and SWFOL-1, represent our species' determination to understand and adapt to our sun's changing behavior. These spacecraft will provide unprecedented insights into how solar activity affects everything, from the edge of our solar system to the upper layers of Earth's atmosphere, while also offering practical early warning capabilities for space weather events. When we expand our perspective to encompass the vast timeline of stellar evolution, our sun's current awakening becomes part of a much grander story. The magnetic dynamo processes that drive solar activity, the nuclear fusion reactions that power our star, and the complex convective flows that transport energy from core to surface, all operate within the framework of a 10 billion-year stellar lifetime that provides the stable foundation for life on Earth. These diverse aspects of solar science are not separate phenomena, but rather different facets of a single, integrated system. The same magnetic dynamo that creates sunspots and solar flares also drives the long-term variations we observe in solar activity. The solar wind that carries space weather toward Earth also shapes the boundary of our heliosphere, determining how cosmic radiation from other stars penetrates our solar neighborhood. The nuclear fusion processes in our sun's core that will eventually transform it into a red giant star also determine the steady energy output that has maintained Earth's climate within the narrow range suitable for liquid water and complex life. The convective motions that transport this nuclear energy to our Sun's surface create the magnetic field variations that produce the 11-year sunspot cycle and longer-term changes like the current awakening. Understanding these connections helps us appreciate why studying our Sun requires such diverse approaches and instruments. No single spacecraft or ground-based observatory can capture all aspects of solar behavior. Instead, we need a coordinated fleet of missions observing different aspects of solar physics, from the nuclear reactions in the core to the interaction of the solar wind with interstellar space. The Advanced Composition Explorer and WIND spacecraft have provided the long-term baseline observations that revealed our Sun's awakening since 2008. Solar Dynamics Observatory captures detailed images of our star's surface activity, while the Parker Solar Probe ventures closer to our Sun than any previous mission to study the origins of the solar wind. Each mission contributes unique pieces to our understanding of how our star works. As an integrated system, this collaborative approach to solar science reflects a broader pattern in modern astronomy, where complex phenomena require multiple perspectives and techniques to understand fully. The same approach that revealed our Sun's awakening, careful analysis of decades of observations from multiple spacecraft, is being applied to understand stellar activity around other stars throughout the galaxy. The technological challenges posed by our Sun's awakening have driven innovations that benefit society in unexpected ways. Improved space weather forecasting helps protect not only satellites and power grids, but also aviation, GPS navigation, and even precision agriculture that relies on satellite guidance. Research into radiation protection for astronauts has led to advances in medical imaging and cancer treatment. Materials developed for spacecraft shielding find applications in nuclear power and medical devices. This pattern of space science driving technological innovation has a long and distinguished history. The same GPS satellites that must be protected from space weather provide navigation services used by billions of people daily. Solar panels developed for spacecraft power systems now provide clean energy for terrestrial applications. Communications satellites that must withstand the space radiation environment enable global internet connectivity. The study of our Sun's magnetic field and plasma physics has contributed to research on controlled nuclear fusion, the attempt to recreate the nuclear reactions that power our star here on Earth. As a clean energy source, understanding how magnetic fields can find and control plasma in our Sun's atmosphere provides insights relevant to designing fusion reactors that could provide abundant, clean energy for human civilization. Climate science also benefits from solar research, though the connections are sometimes subtle. While our Sun's current awakening has minimal direct effects on Earth's climate, the energy output variations are too small to significantly influence global temperatures. Understanding solar variability helps scientists distinguish between natural and human-caused climate changes. The historical record of solar minima, like the Maunder minimum, provides important context for understanding how natural factors can influence Earth's climate system. The philosophical implications of solar science are as profound as the practical ones. Studying our Sun helps us understand our place in the cosmos, revealing the physical processes that connect us to the rest of the universe. The same nuclear reactions that power our star also occur in stars throughout the galaxy. The magnetic dynamo processes that create solar activity likely operate around countless other stars, influencing their planetary systems in ways we're only beginning to understand. As we discover exoplanets around other stars, our understanding of solar physics becomes crucial for assessing their potential habitability. How does stellar activity affect planetary atmospheres? Can life develop and persist around stars that are more magnetically active than our Sun? How do stellar evolution and activity cycles influence the long-term habitability of planetary systems? Our Sun serves as the fundamental reference point for understanding stellar physics. Throughout the universe, every detail we learn about solar structure, activity, and evolution informs our models of how stars in general behave. This knowledge shapes our understanding of galactic chemical evolution, the formation of planetary systems, and the potential for life elsewhere in the cosmos. The international nature of solar science research embodies humanity's collaborative spirit. In exploring the cosmos, scientists from dozens of countries contribute to solar missions, share data freely, and work together to understand our star's behavior. This cooperation transcends political boundaries and cultural differences, united by the shared goal of understanding our cosmic environment. The data from solar missions is made freely available to researchers worldwide, leading to discoveries that no single nation or institution could achieve alone. Students and scientists in countries around the world analyze the same solar observations, bringing diverse perspectives and techniques to bear on common scientific questions. This global collaboration in solar science serves as a model for international cooperation in addressing other challenges facing human civilization. Educational outreach and public engagement in solar science help inspire new generations of scientists and engineers while fostering scientific literacy in the general population. The beauty of solar physics, from the graceful loops of magnetic field lines in coronal images to the aurora displays created by space weather, captures public imagination and demonstrates the relevance of scientific research to everyday life. The long-term perspective that solar physics provides can be both humbling and comforting. Our sun's awakening, significant as it is for our technological systems, represents a tiny fluctuation in stellar processes that have operated for billions of years and will continue for billions more. This vast temporal context helps put human concerns and achievements into cosmic perspective. Yet this same long-term view also highlights the remarkable stability that has allowed life to evolve and flourish on Earth. Our sun's steady nuclear burning has provided consistent energy for geological ages, creating the stable conditions necessary for the development of complex life and human civilization. Even the current awakening occurs within bounds that pose no threat to this fundamental stability. The ongoing story of our sun's awakening reminds us that scientific understanding is always evolving. The research that revealed our star's unexpected behavior since 2008 required decades of patient observation and analysis. Future discoveries will undoubtedly surprise us again, revealing new aspects of solar physics that we cannot currently anticipate. This openness to surprise and discovery is one of the most beautiful aspects of scientific research. Our sun, despite being the most studied object in astronomy, continues to challenge our understanding and reveal new phenomena. Each solar cycle, each space weather event, each long-term trend provides new data that refines and sometimes revolutionizes our models of stellar behavior. As we prepare for the launch of new solar missions and the continuation of existing ones, we can anticipate further discoveries that will deepen our understanding of our star and its influence on our lives. The IMAP mission will map the three-dimensional structure of our heliosphere as it responds to our Sun's awakening. SWFOL-1 will provide improved space weather forecasts to protect our technological systems. Carruthers will reveal new aspects of how space weather affects Earth's atmospheric system. These future observations will occur against the backdrop of our sun's continued awakening, providing opportunities to study solar physics under conditions that haven't been available for decades. The combination of improved instruments and enhanced solar activity promises to reveal new insights into the fundamental processes that govern stellar behavior. In contemplating this integrated picture of solar science, from the nuclear fires in our sun's core to the technological challenges of space weather, from the protection of astronauts to the vast sweep of stellar evolution, we can find both practical knowledge and profound beauty. Our slowly awakening star connects us to cosmic processes that span the entire universe, while also affecting the most intimate details of our daily lives. The gentle persistence of scientific exploration continues to expand our understanding of these connections, building knowledge that serves both practical needs and our deeper human desire to understand our place in the cosmos. Each observation, each discovery, each technological innovation adds to this growing understanding, creating a legacy of knowledge that will benefit future generations of explorers and scientists. And so, as our peaceful journey through the realms of solar science draws to its gentle close. Let us rest together in contemplation of the profound and intimate relationship we share with our slowly awakening star. Throughout our exploration, we have discovered that our sun is far more than a distant source of light and warmth. It is our closest stellar companion, intimately connected to every aspect of our existence through invisible streams of particles and magnetic fields that flow across the 150 million kilometers separating us. This connection becomes ever more apparent as our star continues its unexpected awakening. From what many thought might be a deep, prolonged slumber, the story we have traced together, from the surprising reversal of solar activity in 2008 to the complex challenges of protecting our technological civilization from space weather, reveals a beautiful truth about our place in the cosmos. We are not separate from the universe around us, but rather integral participants in cosmic processes that connect our daily lives to stellar physics, our technological systems to magnetic dynamos operating in our sun's interior, and our future as a spacefaring species to the changing patterns of radiation and particles that flow from our star. This awakening sun touches us in countless ways, most of them invisible and subtle, yet profound in their cumulative effect. Every satellite signal that reaches our phones, every GPS coordinate that guides our travels, every bit of data flowing through our global communications networks, must navigate the changing space weather environment created by our star's increased activity. We have become a civilization whose daily functioning depends on technologies that must constantly adapt to the rhythm of solar variations. The astronauts orbiting high above us aboard the International Space Station experience this solar connection most directly. They live and work within the stream of particles flowing from our sun, their bodies absorbing cosmic radiation that connects them physically to nuclear processes occurring in our star's core. Their experiences, carefully monitored and documented, help us understand how human beings can safely venture into the broader solar system. As our sun continues its awakening, the missions we have explored mapping the three-dimensional boundaries of our solar system Caruthers studying how space weather affects Earth's atmospheric glow SWFOL1 providing early warning of potentially dangerous solar storms represent humanity's growing sophistication in living with our star's natural variability. These spacecraft embody our species' determination to understand and adapt to cosmic processes, rather than simply enduring them. Yet even as we develop ever more sophisticated ways of monitoring and predicting our sun's behavior, we must remember that this awakening occurs within the context of a stellar lifetime that spans 10 billion years. The magnetic variations that create space weather, the particle emissions that challenge our technology, the radiation that requires careful protection for space travelers, all of these represent relatively minor fluctuations in a stellar system that has provided remarkably stable energy output for the entire history of life on Earth. This long-term perspective offers both humility and comfort. Humility in recognizing that our technological civilization, advanced as it may seem to us, must still accommodate itself to natural processes operating on scales far grander than human time scales. Comfort in understanding that our sun's current awakening, while requiring careful attention and adaptation, poses no fundamental threat to the stellar stability that has nurtured life on Earth for billions of years. The beauty of our relationship with our awakening sun lies partly in this balance between change and stability. Our star varies in its activity levels, creating the dynamic space weather environment that challenges and fascinates us, yet it maintains the steady nuclear burning that has kept Earth's oceans liquid and its climate within the narrow range suitable for complex life. We experience both the excitement of discovery and the security of cosmic stability. As we look toward the future, we can anticipate that our relationship with our sun will continue to evolve and deepen. The missions launching in the coming months and years will provide new insights into solar behavior, while advances in space technology will allow us to venture farther from Earth's protective magnetosphere and experience solar influence more directly. Future lunar bases and Mars expeditions will require even more sophisticated understanding of space radiation and its effects on human health and technology. The knowledge we gain from studying our awakening sun will also inform our search for life around other stars. As we discover thousands of exoplanets throughout the galaxy, we need to understand how stellar activity affects planetary atmospheres and the potential for habitability. Our detailed observations of our own star provide the foundation for assessing whether distant worlds might harbor conditions suitable for life. This expanding perspective connects our local relationship with our sun to the broader cosmic story of stellar evolution and planetary system development throughout the universe. The same physical processes we observe in our solar system, magnetic dynamos creating stellar activity, stellar winds shaping planetary environments, radiation affecting atmospheric chemistry, likely operate around countless other stars, influencing the development of life throughout the galaxy. The international cooperation that characterizes modern solar science offers hope for humanity's future relationship with cosmic challenges. Scientists from around the world work together to understand our sun's behavior, sharing data freely and collaborating across political and cultural boundaries. This cooperative spirit in exploring our cosmic environment provides a model for how our species might address other challenges that transcend national borders. The technological innovations driven by the need to understand and adapt to space weather benefit society in unexpected ways. Improved materials for spacecraft shielding find applications in medical devices and nuclear power systems. Advanced electronics designed to withstand radiation help improve the reliability of terrestrial systems. Forecasting techniques developed for space weather contribute to understanding other complex natural systems. Educational outreach and public engagement in solar science help foster scientific literacy and inspire new generations of researchers and engineers. The visual beauty of solar phenomena, from the graceful magnetic loops visible in extreme ultraviolet images to the dancing auroras created when solar particles interact with Earth's magnetic field, captures public imagination and demonstrates the relevance of scientific research to everyday life. The philosophical implications of our relationship with our awakening sun extend beyond practical considerations to touch fundamental questions about our place in the universe. We are made of elements forged in the nuclear furnaces of stars, warmed by stellar energy, and connected through physical processes to the vast community of stars that fills our galaxy. Understanding our sun deepens our appreciation of these cosmic connections. The patient, persistent nature of solar science research mirrors the slow, steady processes we observe in our star itself. Just as solar activity cycles unfold over decades, and stellar evolution occurs over billions of years, our understanding of solar physics develops through the accumulated observations and insights of many researchers over many years. This long-term perspective encourages patience and persistence in addressing other complex challenges facing human civilization. The story of our sun's awakening reminds us that scientific understanding is always evolving. The unexpected reversal of the long-term decline in solar activity that began in 2008 shows that our star still has the capacity to surprise us. Future observations will undoubtedly reveal new aspects of solar behavior that we cannot currently anticipate, keeping solar science dynamic and exciting. This openness to surprise and discovery reflects one of the most beautiful aspects of our relationship with the cosmos. No matter how much we learn about our sun, it continues to present new puzzles and reveal new phenomena. Each solar cycle brings opportunities for discovery. Each space weather event provides new data. Each long-term trend offers insights into processes we don't yet fully understand. As we contemplate our future relationship with our awakening sun, we can find both challenge and opportunity. The increased space weather associated with our star's awakening will require more sophisticated protective measures for our technology and space travelers, but it will also provide more frequent opportunities for scientific observation and discovery, helping us understand solar physics in greater detail than ever before. The gradual nature of our sun's awakening provides time for adaptation and preparation. Unlike sudden natural disasters, space weather changes unfold over months, years, and decades, allowing engineers to design better protective systems, mission planners to develop improved operational procedures, and scientists to refine their forecasting capabilities. This measured pace of change reflects the patient rhythm of cosmic processes. Our growing understanding of our sun's behavior also enhances our ability to appreciate its beauty and significance. When we see aurora displays triggered by space weather events, we can appreciate not just their visual splendor, but also the complex chain of physical processes, from magnetic reconnection in our Sun's atmosphere to particle interactions in Earth's upper atmosphere that creates these celestial light shows. The knowledge that our sun is slowly awakening from what appeared to be the beginning of a deep minimum adds poignancy to our observations of solar activity. We are witnessing a stellar transition that may continue for decades, a gradual stirring that connects us to cosmic rhythms operating on scales far grander than human experience. As our technological civilization becomes increasingly sophisticated in its ability to monitor and adapt to space weather, we develop a more nuanced and respectful relationship with our star, rather than simply enduring solar variability as an unpredictable force of nature. We are learning to work with it to anticipate its effects and to design our systems to function reliably within the natural variations of the space weather environment. This evolution in our relationship with our sun parallels our species' broader development of scientific understanding and technological capability. Each generation builds upon the knowledge of previous generations, gradually developing more sophisticated ways of understanding and adapting to natural processes. The story of our awakening sun becomes part of this larger human story of exploration, discovery, and adaptation. In these final moments of our journey together through the realms of solar science, we can rest in the knowledge that our relationship with our star continues to evolve and deepen. The missions launching in the coming months will provide new insights into solar behavior. The technologies being developed will offer better protection for our space-dependent civilization. The scientists working around the world will continue to unravel the mysteries of our star's complex behavior. But perhaps most importantly, we can find peace in the recognition that we are part of something much larger than ourselves, participants in cosmic processes that connect us to our star, our solar system, our galaxy, and the universe beyond. Our slowly awakening sun serves as a constant reminder of these connections, a beacon that illuminates not just our planet, but our understanding of our place in the vast cosmic community of which we are all part. The gentle rhythm of stellar processes continues day by day, year by year, carrying us forward into a future where humanity and our awakening sun will continue their ancient dance, each influencing the other in ways both subtle and profound, as we gradually expand our presence throughout the solar system and beyond, always connected to the star that makes our existence possible. Good night from the sleepy scientist.